Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the next subject for R-PYQ, that is analog electronics. So we will solve most of the questions from GATE 2020 till 2025 for GATE EE, and few more important, like not all years for EC. I'm not promising all the years, but most of the years, recent years for GATE EC. So all years for GATE EE from 2020 till 2025, and most of the recent years for GATE ECE. Okay, so we will solve all these questions in this whole video, and timestamps, proper timestamps would be provided. Don't worry about that. Everything will be there. So if you are just directly jumping onto this video, if you have not studied anything, maybe it would be a bit difficult for you. So what we have this revision X notes. So you can utilize this to revise all of analog electronics, and then you can come back and watch this video. And also I will mention few other videos that you must watch if you want to comprehensively revise analog electronics. So these are the revision X notes. These are only 29 pages. Okay, complete analog electronics is compressed into 29 pages, but yes, they are a bit smaller to read. So either you can take big printouts, okay, and put it on your wall, stick on your wall, or you can always download the PDF versions and you use the zoom feature and zoom in and read whatever you want to read, right? So all these are properly readable. You can read it if you are able to zoom it. You are able to read it. So if you have tablet, you can zoom it. In phone as well, if you zoom it, you will be able to read every single statement whatever is written. Okay, and also you can annotate over these things. Okay, if you have some writing pad, notepad or something in your tablet. So that is the first thing. So you can revise completely. You can see all the short notes are present over here. And if you want to understand like where can I get these short notes, you can just type revision X short notes by PrepFusion. You will get the complete details on YouTube, or just visit our website prepfusion.in. In the free courses section, the last tab will be revision X. You can click that and download everything. Everything is free. You don't have to pay a single rupees for that. So that was regarding the short notes and revision. Now what more videos can you watch? So in the playlist itself, this is the R-PYQ playlist. I have added few videos. If you see these videos we have added, so how to solve MOSFET in like any MOSFET amplifier problem, you can just watch this 2.5 hours video, and 3 hours video, you can totally revise it. Op-amp in positive feedback, op-amp in positive feedback plus transient, very amazing question. This came ideal differentiator, how does it work, op-amp, and few more challenging questions. So you can use it to revise. And again, already analog electronics R-PYQ, this is a 14 hours marathon which solves all the PYQ questions from 2007 till 2023. So this video will be the continuation part. Okay, and this is in Hindi. So just a bit of disclaimer to all the our students who only understand English language. If they want to, they can watch, but they will not be able to understand, like they will not be able to understand everything, because here these two videos are in Hindi and all the questions are solved from 2007 till 2023. I think for all the branches. WEC certainly he has solved. IN, I don't know, but you can check. Okay, so all these branches Himanshu sir has already solved. So these videos are already there in the playlist. So this will be just the continuation part. So you can start off with this video as well, no problems, or you can start off with this video. I will recommend you start off with this video, then you move on to that video, these two videos, because these are old, these are not the recent questions, right? I have taken the recent questions, so that has the highest probability to come in the next year, and then slowly you can move on to these questions, like these particular videos, because these are lower priority. So first watch this video, then watch those video, but make sure before watching any video, make sure you revise everything properly, because I will not explain every concept in detail in this video. That's not the purpose of this video is to just solve few important questions so that you can revise, and don't just watch the solution. Pause the video, try to solve it by yourself, then see my solution. Okay, so yeah, if you are enjoying this R-PYQ series, and many people have commented for analog electronics, so I'm expecting a good response. So make sure you comment down below so that it can reach more people, and hype the video, like the video, so that this can come in feed of other students as well, because this is not coming in like the R-PYQ series is not coming into feeds of all the students. You guys demanded for analog R-PYQ, so I have bought it. I have completed my promise. This was not even promise, so I have completed that. Now it's your responsibility to share it, like it, comment down below whatever you felt like. You enjoyed it, hated it, whatever you felt, you can do that, right? So that just helps us to reach more students, and more students can take the benefit out of this. So yeah, let's begin with diode circuits. So let's solve this first question. Consider the diode shown in the below figure the diode obeys this current voltage characteristics. It is nothing but the forward biased equation of the current equation of the diode, right? And of course this will work as negative, this will work in negative bias as well. If Vd is very high in the negative direction, so this will be approximately 0, so your Id will be minus Is, which will be very small. So all these values are given accordingly. Vd, Id are the voltage and the current across the diode. The circuit is biased so that the V is greater than 0. Okay, voltage is greater than 0 and the current is negative. Okay, current is negative. If you had to design this circuit to transfer maximum power from the current source, right? If you have to design this circuit to transfer maximum power from the current source, so from the current source we want to drive the maximum power to a resistive load not shown. So basically there will be a resistive load that will be connected, that is not shown at the output. What values of R1 and R2 would you choose? Okay, what values of R1 and R2 would you choose here? So if I see, sorry, this is RL, right? This is RL. Now the thing is, also they have told me that the circuit is biased such that my V is greater than 0, but this current I is negative. Okay, this V is greater than 0, this V is positive, but current is negative. So current actually I is less than 0, current will flow something like this. Although this would not make any difference to the what do you call the power, because power is I square R. Okay, but it is biased such that this current is negative. Okay, that is cool. If this current is coming from here, right, and this current also is coming here, then certainly some current will flow through here as well in this direction. Now if current flows through this resistor in this direction, correct, because current will not be able to flow like this, because if current is flowing like this, then you are saying because for the, if the diode is turned on, current will flow like this only, right? Okay, okay, before this let us think of something. So let's see the options. They are saying large R1. So if R1 is very large, what will happen? If R1 is very large, right, so current from this branch will be lower. Let's assume for a second, just assume there is some current here, I. Okay, there is some current Ix, and this Ix will be divided into these two resistors, right? So can you calculate your I in terms of Ix? I would be, just let me mark the proper direction now. Okay, although I know it is negative, that is fine, it will not change our answer. I would be equals to Ix into R2 divided by R2 divided by R1 plus R2, right? Now I want this I to be maximum, correct? I want this I to be maximum, right? If I want my I to be maximum, what needs to happen? If I want my I to be maximum, what needs to happen? So basically, this, right, this R2 must be very high, R1 must be very low. If R1 is very high, keeping R2 constant, what will happen? This I will reduce, which I don't want. Obviously it makes sense, right? If this has higher resistance, obviously the current will choose the lower resistive path, it will choose this path. That is point 1. So R2 needs to be very high actually, correct? R2 needs to be very high. R1 cannot be very high, R1 can be very small. If R1 is smaller, then of course your I will increase. So R1 has to be lower, R2 has to be very large. R1 smaller, R2 has to be very large. Okay, so you might think, sir, what about the diode? Yes, you are correct. What about the diode? So if you see, if you assume your R1 to be very small and your R2 to be very large, you observe that this current, right, is, let's say your R2 is very large compared to R1. So R2 by R1 is approximately equals to, okay, sorry, R1 by R2 is approximately equals to 0, right? R1 by R2 is approximately equals to 0. So then I can simplify this equation. This equation would be Ix. I can take common R2. If I take common R2 from the denominator, this will be R2 R1 plus R2 plus 1. So this will be equals to this will be equals to approximately 1, right? Because this will be 0, right? R1 by R2 approximately will be 0. This will be approximately 1. So your I current becomes constant, that is equals to Ix only. Okay. Now if your this current is approximately constant, what will happen? What will happen? What will be the current through here? Can you tell me what will be the current through here? So your I is equals to Ix. Whatever is your current through here, that is Ix only. So current through here is approximately 0. If it is 0, no current will flow through this. Like, yeah, some current will flow, that is minus Is. If this is 0, right? Actually, yeah. If this is 0, no current will flow through this. So if what happens? Approximately this Vd becomes 0. Vd becomes 0. And if Vd is 0, the voltage across the diode is 0. That means this is e raised to power 0 minus 1, that is 1 minus 1, that is 0. So it takes no current. Whatever current is coming from here, I1, all of it is going to Ix, and all of that Ix current is going to I. Right? So maximum power is getting transferred in this condition. So sometimes if you don't know how to start the question, start with the options. So in this case, there are a lot of things we could have done with a question with a solution, right? But the bottom line is we start with the options, we check the conditions, and then we saw, yes, this makes more sense. Why it does makes more sense? Then I dug more deeper into it. Then I saw, okay, this is taking no current. The voltage approximately 0. So all these things are very, very important to understand. Okay. So yeah, that makes sense. And trust me, you will see any solution, you will not be able to understand why they take this question. Why they take this answer. You will not be able to understand it. Okay. Okay, sorry, not option B. I'm sorry. We need large R2. We need large R2, right? So R2 must be large and R1 must be small. So option D is correct. Sorry, R2 must be large and R1 must be small. I'm sorry, I was taking option B. I'm sorry. Yeah, R1 must be small as we discussed here, and R2 must be large. So check the options as well. In a hurry, you might take something else. So don't be like me. Okay. So I can make mistakes because I am explaining, right? So I can do that, but you cannot make the silly mistake. Yeah, let's solve this question. So in this question, a non-ideal diode is biased with voltage of this minus 0.03 volt. A diode current I1 is measured. So a non-ideal diode is biased with a voltage of minus 0.03 volt. Okay. The diode current I1 is measured. The terminal voltage. So do you remember what is the ID equation? ID equation is this. You will have to remember, it is Is e raised to power eta V D upon Vt. Minus 1. Okay. So this is the current equation, right? This is the current equation. Now how can we solve it? So current is this measured. Now they are biasing it this voltage, that is fine. The thermal voltage is given. The ideality factor is 15/3. So your eta basically is the ideality factor. Right? The voltage in V at which the measured current increases to 1.5 I1. Okay, that is what they're asking. What is the voltage at which the measured current increases to 1.5 times the previous current? So when my I1, so when my ID was equals to I1, the equation was Is eta is 15/13. Ideality factor is 15/13, and your Vt is 26, right? sorry, Vd upon eta Vt, sorry, don't forget the equation. It is Vd upon eta Vt. It is not eta into Vd upon Vt, no. So you will have to remember the equation. So Vd upon eta Vt. So eta is 15 by 13 into 26. So 15 by 13 into 26 is nothing but 15 into 2, that is 30. And yes, it is 30 millivolts. So hence I have to write in the numerator millivolts. I should write the same unit in the numerator as well. So what is the unit in the numerator? Vd. Vd is given to us as 0 minus 0.03 minus 0.03 volts. So I can convert this into millivolts, right? So if I convert this into millivolts, this will be equals to minus 300. Sorry, not 300, minus 30. So this will be essentially minus 1 only. That is the first equation, that is minus 1. So your equation gets converted into Is e raised to power minus 1 minus 1. And your current in the second case, this will be Is into e raised to power Vd. Vd is Vd, okay. Yeah, so Vd in the second case, that is what they are asking me, right? What is the voltage V? So yeah, let me write this voltage as V only, and let me write this eta into Vt, that is equals to 30 only, right? This is 30. Remember, your voltage will be coming out to be in millivolts, minus 1, and I know I2 is nothing but 1.5 of I1. 1.5 of I1. So yeah, if I solve this, I2 by I1, this will be 1.5 of I1 divided by I1, that is equals to Is into V divided by 30 minus 1 divided by Is into e raised to power minus 1 minus 1. So this will be cancelled. This will be 1.5. So 1.5, whatever is this value, let me compute this value. This would be equals to minus 1 into 1.5. So this will be minus 9.4 minus 9.5 minus 9.5 plus 1, and then take the log of this, that is minus 3. So V by 30 is minus 3 into 30 divided by 1000 to convert this into volts. So approximately, if you like, this is just calculation. So your voltage comes out to be, remember, this is in millivolts, right? Millivolts. So approximately it comes out to be minus 88.8 millivolts, or I can say minus 0.09 volts. Okay, so minus 0.09 volts is present in option B. So option B will be the correct answer. So make sure you remember this equation. And ideality factor, if nothing is mentioned, you will assume it to be 1, and Vt, if nothing is mentioned, you will take it to be 26 millivolts. That's cool. So these things can be asked. So make sure you remember the equation. It's very important that you don't forget the current diode equation. So yeah, let's move on to the next question. This is the next question. Seems like a rectifier kind of circuit, but let's see. In the circuit shown, the input voltage Vi is sinusoidal, AC voltage RMS is 230 volt plus minus 20%. The worst case peak inverse voltage seen across any of the diode would be. What is the worst case peak inverse voltage if I have a capacitor at the load connected, right? So worst case peak inverse voltage, let's assume that this R is not even there. Let's assume that R is infinity, correct? If I assume my R to be infinity, what will happen? Or if I assume my omega frequency of the voltage to be very small, right? Sorry, very high, then this capacitor will dominate the resistor. So what will happen is, we know the peak inverse voltage, right, is basically for a full bridge diode rectifier, it is Vm, correct? It is plus Vm. Now in our case, what is the maximum peak voltage? Because they have told me RMS value is this plus minus 20. So peak value would be Vm would be root 2 into 230 into 1/2, correct? Root 2 into 230 into 1/2. So this would be equals to 230 into 1/2 into root 2. So 390.29 390.323 volts. Okay, this is your answer basically. Round out to 2 decimal places, so it will be 390.32. So these things you should know already, that the peak inverse voltage for a full bridge rectifier is Vm. If I assume this to be a purely capacitive load, so what will happen, like after, if this clamps to some voltage Vm, then if so, what happens is essentially is that at any point of certain time, let's say this capacitor has totally clamped to voltage Vm, correct? If I assume my capacitance to be very, sorry, if I assume my frequency to be very high, so capacitor will dominate, so this can clamp to voltage Vm. Okay, that's my assumption. If this clamps to voltage Vm, and just at the starting when this Vi, let's say, turns on this diode D1 and this diode D2, okay, so this path becomes short circuit. So if this path becomes short circuit, if you measure the voltage across the diode, this will be plus Vm, and this is the maximum voltage, maximum inverse voltage across this diode, because this diode is reverse bias. If you could not understand anything whatever I said, that means you need to go and study analog electronics. This question is the revision question practice session. I will not be able to explain every single concept here. That's the problem. I can explain that, but this video will go long. But that's not the point of this video. This video is for those guys who have studied analog electronics and they just want to have a quick revision, whatever they know, right? Whatever are the important points or whatever extra points that I can conclude, I am concluding. So if you are not able to understand this, you have to go and watch the full course, right? Those videos that whichever I mentioned, you have to go to YouTube, watch those, and then only come back here. Okay, so answer would be 390.32. So let's move on to the next question. This is the next question. In the circuit shown, a 5 volt Zener diode is used to regulate the voltage across RO. The input is an unregulated DC voltage with a minimum value. So input minimum value Vi minimum is 6 volts and Vi maximum is 8 volts, right? Vi minimum and Vi maximum is 8 volts. The value of RS is 6 ohms. The value of RS is 6 ohms. The Zener diode has a maximum rated power dissipation. So this RS value is 6 ohms maximum. So PZ max, maximum power dissipation across the Zener diode is 2.5 5 volts. Assuming the Zener diode to be ideal, the minimum value of RO would be, okay, maximum power dissipation across the Zener diode is 2.5 volts. Minimum value is this, maximum value is this. So it is a 5 volt Zener diode, right? So voltage across the Zener diode VZ is 5 volt. So can you tell me what is the maximum current that the Zener diode can take? So IZ max shall be equals to 0.5 ampere, right? That is what your IZ max is equals to, correct? That is what your IZ max is equals to. Now we got our current. Assuming the Zener diode to be ideal, the minimum value of RO would be. So they are asking me what is the minimum value of that RO can take. Okay, so we want to regulate it to be at 5 volt, right? So if I reduce my RO, do you know what will happen? If I reduce my RO, what will happen actually? So what is the current across the load? IO would be the voltage across the load, that is 5, that is fixed according to the Zener diode, upon RO. So if I reduce my RO, this current will increase. Basically they want to know about this condition, right? So when my RO is minimum, your IO will be maximum, and when your IO is maximum, then your IZ will be minimum, correct? Because what is happening? What is this current? This input current. This input current, let's say I in is equals to II, that is equals to V in minus Vz, that is constant, upon Ri. Ri is also constant, Vz is also constant, only that is not constant is Vi. That is equals to uh, this current Iz and this current. So Iz plus Vz plus R. Iz plus Vz by R. So Vz by R, again we want this current to be, so we want our RO to be minimum, so this will be maximum current. Now if this current is maximum, right, and we want to reach to the absolute limit of Iz, right, absolute limit. So Vi is variable, so I would want this to be also minimum, right? When this is minimum, then only your Iz also will be minimum, because I want to reach to a limit. They are asking me certain limit, right? That is the point. Okay, so for an ideal Zener diode, the minimum Zener current will be 0 amperes, because in 0 amperes it will be activated. That is the minimum Zener current for an ideal Zener diode. So Iz minimum will be 0, Vi minimum would be equals to 6 volts. 6 minus Vz, that is 5, right? Vz is 5 upon Ri. Ri is also Ri is 6 ohms. So this is my Imax. Imax is nothing but Vz. Vz is 5 upon RO min. So your RO min would be equals to this will be 30. Yeah, 30. Now is it in ohms or kiloohms? Ohms, because everything is in proper units, everything is in ohms and volts, so this also will be in ohms. So your answer that the minimum value of RO that is possible is 30. If I go below 30, what will happen? If I go below 30, right, this current will increase, then I cannot go. So if I go below 30, this current will increase, right? If I go below 30, this current will increase, and if this current increases, then for voltage, so if the voltage is 8 volts, then maybe I will be able to send that I will be able to deliver that much amount of current. But if the voltage is 6 volts, let's say at a certain point the voltage is 6 volts, right, and you keep a resistor lower than 30 ohms, let's say 25, if you do that, your Zener diode will not be turned on, right, because your Iz minimum will be not 0. So it will be something, it will come out to be something negative, which is not possible, right? Hence your Zener diode will not turn on, and if your Zener diode does not turn on, this will simply work as a voltage divider. Then your voltage will not be regulated. Got my point? The point being is, you might have a doubt, sir, you chose 6 volts here. What if you choose 8 volt here? If I choose 8 volt here, then you say that even, so let's choose that, right? Let's do that. That let's assume that RO is, okay, just give me 1 second. Why is this? Okay, just pencil. Yeah, RO is, let's say, 25 ohms. What will happen? If RO is 25 ohms, what will happen? Let's assume for a second that this voltage is some V minus 5, right, upon 6, and you assume your Zener diode, it's the minimum current, that is 0 only, plus you assume your Zener diode to work. You are assuming your Zener diode to work, okay? You're assuming that. So that's why your Zener current is minimum. That is equals to V upon 25. Just a thought, you are assuming your Zener diode to work, that's all. So this will be equals to so that is V is, okay, Zener diode, that is not V, sorry, that is 5, right? 5. Okay, so that is 1 by 25, 1 by 25, sorry, 1 by 5, 1 by 5, this 6 will go there, there is 6 by 5 plus 5. So your V is coming out to be 6.2 volts. So if your voltage is 6.2 volts, then only this circuit will work. Okay, if a voltage is 6.2 volts, then only this circuit will work. What if your voltage is 6 volts? What will happen if your voltage is 6 volts? If your voltage is 6 volts, then you will come into some problem. Then this current will become negative, which is not possible. Hence, Zener diode will be turned off. If Zener diode is turned off, what will happen? This will simply work as a voltage divider. Your voltage will not be regulated. Got my point? So that is the thing. That is the reason why I chose the minimum value, because I want to reach to a threshold. So for the minimum value possible, what is the minimum resistor, right? For which the Zener diode will always be on. So these are the cases basically. I hope you got the point, right? So RO minimum is 30 ohms. We got to our answer. Let's now solve this question, right? Here we have been given a waveform. Waveform is shown in solid line, and it is obtained by clipping the full wave rectifier sinusoid. The ratio of the RMS value of the full wave rectified waveform to the RMS value of the full wave clipped waveform, right? So full wave rectifier waveform, how does it look? It simply looks like this, right? Rectified sinusoid. So what is the RMS value? RMS value actually is same as the not rectified version, that is Vm by root 2, where Vm is the peak value of the sinusoid. Okay, these things are very simple, because for a non-rectified case, because anyways you are squaring it, so this negative area anyways becomes positive. So ultimately it does not matter. It does not matter. Okay, so that is the thing. Now, if I'm clipping it here, what is the RMS value? For this, you will have to go by the long method. There is no shortcut over here. There is no shortcut, unfortunately. Okay, so what you can do, you can break this into 3 parts. What kind of 3 parts? So first part should go from, first part is a sinusoid from 0 to pi by 4. Second part, if you see, is just a square waveform from pi by 4 to 3 pi by 4, and the third part is again a sinusoid from 3 pi by 4 to pi, and this cycle continues and repeats. Correct? Yeah. So now if we solve this, so now if I solve this, that just give me a second now. Yeah, so I need to find out the RMS value of this part, and this part. How shall I find it out? I'm just thinking, do I have any shortcut? Just thinking about that. No, we don't have any shortcuts. We don't have. So we know one thing, right? So these three. So if you have studied signals, you will remember that my x1 of t, x2 of t, and x3 of t are all orthogonal. I will not explain what does orthogonality mean. My expectation is you already know all these things. If these three signals are orthogonal, then the RMS value of the overall signals would be equals to under root of x1 of RMS whole square plus x2 of RMS whole square plus x3 of RMS whole square. Got it? So, yep, this will be the answer basically. So, how do I compute x1 of RMS? It's very simple, and x1 of RMS, technically x1 of RMS will be equals to your x2 of RMS, x3 of RMS, because it is symmetrical. Okay, these things can be you can see from symmetricity. Cool. Yeah, and x2 of RMS is very easy to compute, but let's first compute one thing, x1 of RMS. So this will be equals to, so what is the period of this? 0 to pi, correct? So 1 by t, 0 to pi, uh, x square. So root means square, right? So first I will square the waveform. So what is this waveform? This is simply Vm square sine square omega t, right? This is the waveform. Vm sine omega t is the waveform. If I square it, it will be Vm square sine square omega t d omega t 0 to pi, and then of course you will need to root mean square. First you will square, then you will take the mean, and then you will take the root. That's what root mean square means. So yeah, if I solve this, under root pi will be there at the front, Vm will be there, okay, and this will be, now what is the integration of sine square? So we know cos square t minus sine square t equals to 1, correct? So I want to replace sine square t, so this will be 1 minus, okay, 1 minus sine square t, that 2 will go there, okay, 1 hold on a second, this will be 1 minus sine square t, right? Sorry, what am I doing? This is cos 2t, okay, I almost forgot the relation, identity. Yeah, cos square t minus sine square t equals to cos 2t. So 1 minus 2 sine square t will be equals to cos 2t, or I can say 1 minus cos 2t divided by 2 is equals to sine square t, right? I'm writing this in rough because my expectation is you already know all this and you can do it on your own, okay? I'm not writing them in proper fashion because in the exam as well I will solve like this only. So here this will be 1 minus cos 2t by 2. Sin square t can be replaced with 1 minus cos 2t by 2. Ultimately, if we are integrating from 0 to pi, right? What is the period of this cos 2t? The period of this is pi only, correct? The period of cos 2t is pi. And if I am integrating any cosinusoid or sinusoid over a period, that is 0. So ultimately, all I am concerned about is this part, right? Now, one thing we forgot, while, so the period is this, right? But what is the limits? It will go from 0 to pi. Will it go from 0 to pi? No, right? I'm only talking about x1, and x1 only lies in the range from 0 to pi by 4. x1 only lies in the range of 0 to pi by 4. So actually, we shall not integrate from 0 to pi, right? We shall integrate from 0 to pi by 4. So then in that case, this integration will not be 0. So we will have to solve this properly. So be very careful how to calculate RMS values. So this will be 0 to pi by 4, which is okay, this will be omega t by omega t. So simply this will be 1 minus cos 2 omega t by 2. That is the integration, correct? And limits would be 0 to pi by 4. Okay. So yeah, Vm by under root pi. So 0 pi by 4, so pi by 4, 1 by 2 can come outside, root 2, right? Yeah, this can come outside. Pi by 4 minus, now if I put pi by 4 here, so cos 0 is 1, right? So minus cos 0 is 1, certainly it is 1. What about hold on a second. Okay. Yeah, we'll have to integrate this, right? Don't forget, you will have to integrate this as well. I'm just in a hurry, I'm in a super hurry, right? Don't forget, you will have to integrate this. I'm sorry. So if I integrate this, this will be pi by 4. That is no problem. One integration of 1 by 2, 1 by 2, 2 is taken at the in front, right? So this is pi by 4. What about this one? So integration of minus cos will be sine, right? If I'm not, will be minus sine. Yeah, integration of minus cos will be minus sine, and if I put sine 0, that is 0 only. If I put sine to omega t equals to pi by 4, this will be sine pi by 2, that is 1. So this will be actually 1. Okay, so your value comes out to be Vm by Vm. Okay, let me keep it, actually let me keep it like this. This is your value basically. Now the thing is that this is just x1 RMS, right? And I have already discussed that your x2 RMS also will be same, correct? X2 RMS also will be same, that is this only. So let us put everything in this equation. Sorry, not x2, x3 RMS also will be same as x1 RMS. Let us find out x2 RMS. It's very simple. If you have studied signals, this is nothing but a rectangle, right? And we know what is the RMS value of a rectangle. It is simply a square tau. A square tau is, sorry, it is the energy. Uh, it is the energy, right? Energy is a square into tau. Tau is pi by 4. A is, in this case, what is A? How do you calculate A? A is this, right? That is my A. What is A? 0.707 Vm. That is nothing but root 2 into Vm. That is my A. Root 2 into Vm. So this would be root 2 into Vm whole square into tau. Tau is the width of the rectangle, that is pi by 2. That is pi by 2. So this is pi by 2. Now if this is pi by 2, then this would be Vm square. Vm square, and okay, this is the area, right? And what is the power? Power would be energy upon time period. What is the time period? It repeats after every pi, right? That is the time period of this waveform, because the whole waveform has a time period of pi only. So divide by pi would be my power. Now if I know the power, can you calculate the RMS value? Certainly yes. So RMS value would be under root of power. So that would be under root of this, right? Okay. So if you are not able to understand this, then you will just solve this basic thing. You do this, right? So, but that will be okay. You have to define your signal into 3 different definitions, and then you will have to solve. That is bit tedious. You can solve it. Okay, you will get the same answer, but we are solving it in a bit easier, like not easier, in a faster method. This is also not easy if you don't know the concept, but my expectation is you have bit of knowledge about signals. So this will be equals to pi will be cancelled. This will be 2 Vm square root. So so 2 will be cancelled. This will be Vm only. So your RMS value here, it comes out to be Vm only, under root Vm. So not even under root Vm, it is Vm only. Okay, it is Vm only. Correct. So yeah, let's now try to solve this part. Right, we know all the values. Now let's actually calculate the RMS value of the whole waveform. That would be equals to under root this whole square, right? Because this is the x1 RMS into x2 RMS whole square. So this will be basically this whole square, that is this whole square into 2, because I am considering both x1 and x3 plus obviously the this RMS value whole square, that is Vm square only, x2 RMS whole square, that is Vm square. So this is Vm square whole under root. So this would be equals to Vm by pi. Okay, Vm by pi into pi square by 4 minus 1 plus 1 minus, okay, let me solve this anyways. What is this value? Pi by 4 minus 1 whole square divided by pi plus 1 whole under root. So this actually comes out, and this should be okay. This I am squaring, right? This also will be squared. Yeah, sorry. So this will be actually 1.007 Vm only. So your XRMS approximately comes out to be 1.770 Vm. I'm just thinking whether everything is correct here or not. Just give me 1 second. This is multiplied root 2 times Vm. How is this coming out to Vm? This should not be. So I'm dividing by pi, I'm multiplying by pi by 2. Oh, sorry, I'm extremely sorry. This is not root to Vm. I know you guys are screaming in the screen. Sorry. Bad habits. So this is the inverse, right? This is 1 by root 20 Vm. I'm extremely sorry. That's what I was thinking. How is this coming so high? Sorry. This will be 1 by root 2, right? Sorry. That's what happens. You make silly mistakes. This would be 1 by root 2. And if it is 1 by root 2, then things will change. This will be 1 by 2 into 1 by 2. Pi will be cancelled. So this will be Vm by 2 actually. I'm extremely sorry. This will be Vm by 2, right? If it is Vm by 2, so this will be Vm by 4 actually. Okay, Vm by 4. So this is Vm by 4. Okay, still this comes out to be very small value. Oh no, this is fine. So so this would be pi by 4 minus 1 whole square. 2 will be cancelled, divided by pi plus 0.25 whole under root. This comes out to be 0.518, 0.514. 0.514. So okay, I'm just thinking whether I'm doing everything correctly or not, because I'm seeing some sort of problems. Okay, this is 0.512 and that is by root 2. Just give me 1 second. So this will be whole squared will be converted by 2, 1 minus 2 cos of 2 omega t by 2, 0 to pi by 4 we have to compute because we are going from 0 to pi by 4 only. So 0 to pi by 4 would be, this 2 can go outside, that is in the under root. This would be pi by 4 minus sine of, so minus sign would be there, right, if I'm not mistaken. What is the differentiation of cos minus sine? What is the integration of, it is plus sign only, huh? That is correct, it is plus sign only. So I'm just thinking, uh, uh okay, 2 pi by 4 minus this, pi by 4, yup, pi by 4, is it minus 1? Yes, it is minus 1, it is minus 1, yes. So this is minus 1. Now if I square this, right, as the RMS value of both of them are same, so if I square this, it won't matter. So this will be pi by 4 minus 1. Okay, pi by 4 is almost like something 0.7, 0.3 something. If I square it, that will be higher. This will be 2 pi squared, 2 will be multiplied, 2 will be multiplied. Okay, and this will be Vm square into pi, that is the width, that is the period. No, everything seems correct from my end. Everything seems correct. So this is Vm by pi. Let me just check once more. So whole square whole under root. This XRMS is this. Now what about your this was your XRMS actual crypt, right? They have asked the ratio of the, they have asked the ratio of the full wave rectified waveform, that is Vm upon root 2 divided by the clip waveform. So it would be, basically they have asked the ratio of Vm by root 2, the clip waveform, divided by the RMS value of the actual waveform, that is 0.5144 Vm. So this would be equals to this into 0.707, that is 1.34, 1.375. So according to me, the answer should be 1.37. This should be the answer of the question. Yeah, sorry, I was just rechecking my answer, and I wasted so much of time understanding where am I doing something wrong. Okay, I know you guys were screaming at the screen, but when I integrated, right, that's why you should never skip a step. Okay, in the exam hall, don't skip a step. So when I integrated this cos 2 omega t, I forgot to divide by 2. I forgot to divide by 2. Okay, what do I mean by it? So in what is integration? So we have to integrate with respect to d omega t, correct? Integrate with respect to d omega t. So never try to like be in a hurry if you are in the exam hall. So this will be, this is Vm by under root pi. This is fine. So this will be equals to omega t minus cos. So integration of cos omega t would be what? 1 by 2 is already there at the front, right? I can take the 1 by 2 outside the integration. indication of cos 2 omega t would be minus sin 2 omega t by 2. And that is where I made the mistake. I forgot to divide by 2. Everything I'm doing, but I'm forgetting to divide by 2. And that's why I was thinking, why am I making a mistake? Okay, don't make this. I was wasting so much of time in calculating where exactly the mistake is happening, right? So Vm by under root 2. So Vm by under, so this will be actually 1 by 2. That's where I had made a mistake. So this, right, will change. Values will change now. So this will be pi by 4 minus 0.5 whole square, then plus 0.25, then taking the under root. So this comes out to be 5.757 Vm. Okay, so this will change to 5757, this into 0.707. So this comes out to be 1.228, and they have asked us to uh, round off to 2 decimal places. So this will be 1.23. Okay, so 1.23 should be your answer for this question. So this is where I was making a slight error, so be careful. So let's move on to the next question. This is the next question, right? So for the circuit shown with ideal diodes, the output will be what? So the diodes are ideal. So if I see, when this voltage is positive, right? So when Vin is positive, that means what? Basically means this node potential is higher than this node potential, right? So if this node potential is higher, let's assume that your diode is on. If your diode is on, so this node potential is higher, current is flowing, right? Current is flowing from here to here. So current is properly flowing, right? So this node potential also will be somewhat higher than this node potential. Then D2 and D1 both will be on. So when, and that makes sense, right? If I assume D1 and D2 to both be on, I see the current is in the proper direction. Current is flowing from P to N for both the diodes. So for both the diodes, during positive half cycle, it is on. During negative half cycle, what is happening? During negative half cycle, if you see that this point potential will be lower, if you assume for a second that this diode is off, if this diode is off, there is no current. So here the potential is, let's say this is reference, this is 0 volts, and this is some, now this point potential is lower, right? So that means negative point potential will be higher. That is what this negative means. It will be just flipped. So if it was plus minus 5 previously, now it will be minus plus 5. So this point potential will be higher. That basically means that this diode will be turned off. If this diode is turned off, basically, then then basically what will happen? Both of them will be off. So when both of them are off, my V out is simply 0. So my V out is equal to V in when my V in is greater than 0. Correct? Very simple and easy to understand. Otherwise, it is always 0. So the voltage transfer characteristics is this, right? Of V out with respect to V in. Whenever your V in is positive, both the diodes are on. So these are essentially short circuited. They are ideal diodes. So whatever is the potential here, same potential will be applied across the R1, and that is where we are measuring the output voltage potential. So that's why my V out will be equals to V in. Let's solve the next question. So for this, option A is correct. Let me delete this. Yeah, this is the next question, that all the elements in the circuit are ideal. Which of the following statements is true? When switch S is on, both diodes D1 and D2 conduct. So both of these diodes will conduct when switch S is on. Okay, when the switch S is on, both D1 and D2 will conduct. Okay, and D3 is reverse bias. So they're basically asking me what are the conditions of diodes when switch S is on or off. So if I assume for a second, if the switch is on, 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 what will happen? Okay, so let's take this condition, both D1 and D2 will conduct. If both D1 and D2 conducts, both of them are on, so this is essentially short circuited, right? And this point potential is plus 20 volt. Okay, fine. If it is short circuited, this point potential is plus 20 volt, and if I assume this to be reference, So this is 0 volts, right? So for this diode D1, this point potential is plus and this point potential is 0, that is almost minus only. So this has a positive potential across it. So this is forward bias, that is correct. But still I am not able to prove that whether this will be forward biased or not. How can I prove it? Okay. So if I assume my D3 to be off, if D3 is off, so the first statement tells me that D3 must be reverse biased when S is on. So if D3 is off, then this 2 ampere current has two paths. Either it can flow in this direction or in this direction. Certainly it cannot flow in this direction because D3 is off. And of course, if D1 is on, current can never flow from N to P if a diode is on. It will always flow from P to N. So certainly this 2 ampere current has to flow in this direction. And again, this supply current is 0 ampere because this D3 is off, hence this current is also 0. So all of the current will flow here, that is 2 ampere. Right, all of the current will flow here, that is 2 ampere. Now all of the current flows here, that is 2 ampere. Now how do I, so this current is 4 ampere, right? 4 ampere. So the current from this battery is 4 ampere. So whatever current comes out of from the battery, same current should come in. So this also current should be always 4 ampere. Correct? Certainly then this current will be what? This current will be in this direction 2 ampere. Simple KCL. So if this current is here 2 ampere, then certainly this current has to be in this direction 4 ampere. If this current has to be 4 ampere and here also 4 ampere current is flowing, so diode D1 has 0 amperes of current. And whenever we assume a diode to be in forward bias and we see that the current is 0, that means it is wrong, right? That means option A is certainly not true. If current is 0, that means your diode may be in reverse bias. You cannot surely say, but your diode may be in reverse bias, right? But certainly one thing we can conclude, okay, if switch S is on, right, and in the second statement they are telling me if switch S is on, D1 conducts and both D2 and D3 are reverse biased. Okay, they are telling me both D2 and D3 are reverse biased. So let's see that now. So D2 and D3 both are reverse biased. So if D2 is off, okay, if D2 is off, right, let me just remove all this. Let's take this assumption, D2 is off, D3 is off. So if D2 and D3 both are off, let me remove them. Okay, so if this current is 2 ampere, right, and no current is coming from here, so all of this 2 ampere should come from here. This is the 2 ampere, right, and this switch obviously is on. This switch obviously is on. So okay, 2 ampere is coming from here. So this 2 ampere can have this path and this path. Again, current, this they are telling me D1 is on, right? So if D1 is on, that basically means that current has to flow from this direction, from here to here, right? That means from here 4 ampere current must flow. 4 ampere current must flow, right? Because this does not have any path. So if 4 ampere current is flowing from in this direction, and in this direction 2 ampere of current is flowing, then from this switch 6 amperes of current will flow. That is fine. 6 amperes of current will flow. Again, through the battery there is 0 amperes, so here no current will flow. All of the 6 amperes will come here, and we know this 4 amperes of current is coming out from here. Hence the remaining 2 amperes will go to this battery, and all the KVLs and KCLs are absolutely satisfying, and this D1 diode has positive current from P to N. That means D1 is on. Whatever our assumption was, all these are correct. What about the potential? Potential you will not be able to comment regarding D2 and D3 because here there are current sources. Will be a bit difficult to comment, but you can certainly say what is the potential across the diode D3. Right, this is my P, this is my N for the diode D3, right? So I see it is reverse bias. Certainly D3 is reverse bias. Can I comment regarding the potential of D2? Yes, you can. So this point, so D2, right, this let's say is point A, and this point is same as shorting as this reference, right? So this point is reference. Again, this is my P and N. Again, I see Pn has higher potential than N. Then certainly your D2 also will be reverse bias. So certainly option B is absolutely correct. So you go by if you have more than 2 diodes, then you go by the options. Certainly option B is correct. Because it is a MSQ, we will have to see the other options as well. Let's see the option C and D. So when switch S is off, D1 is reverse bias, both D2 and D3 conducts. So when switch S is off, there is no current through the switch, and they are saying me that D1 is reversed biased, right? So if D1 is reverse biased, right, this will be open circuit. D2 and D3 conduct. So D2 and D3 conduct, right? So D2 will be on, D3 will be on. Okay. So D2 and D3 will conduct. Now through here the current is 0. So current here would be 4 ampere, right? And through here current is 2 ampere. So current through here would be 2 ampere. Just give me a second. Through here current is 2 ampere. So current through here is 4 ampere. We certainly know that, right? So again, this has 0 amperes of current because switch is off, and this has to have 2 amperes of current, and that 2 amperes of current will be coming from this battery, that will be coming from the diode, and that 2 ampere of current shall be coming from here. Hence, if I apply the KCL, that means this shall have 0 amperes amount of current. So every KCL KVL satisfies, right? If you see that the all the KCLs are satisfying, what all the conditions are satisfying. Now if you want to measure the potential across the diode D1, so if you want to measure the potential across the diode D1, if you see this point is connected to plus 20, right? So the P is connected to plus 20, and the N of diode D1 is connected to plus 40. So again, N is at higher potential than P, and both their reference are same. Certainly then D1 will be reverse bias. D1 will not be on. So the option D is automatically eliminated. D1 cannot be on. Okay. So you can check the option D. You will see that it is not satisfying or matching any of the conditions. So for diode to be forward bias, current must flow from P to N. For a diode to be reverse bias, the potential across the diode must be negative or must be less than the cut-in voltage. So that's why option B and C would be correct in this question. Let's move on to the next question. So this is the next question, right? So next question is this: in the given circuit, the diodes are ideal. In the given circuit, the diodes are ideal, right? The current I through the diode D1 in milliamperes would be. What is the current I through the diode D1, right? So yeah, that's pretty simple. They just simply want me to calculate this current. So if you assume one thing, let's assume that everything is off. Okay, both D2 and D1 are off. If D2 is off, right, no current flows here, that means this will work simply as a voltage divider. So this point potential will be 5 volts. If D1 is also off, right, so no current flows here, so this ground can come here. Again, no current flows here, so this ground can come here, right? So this point is 0 volt, this point is 5 volt, then D2 certainly has to turn on. So our assumption was wrong. So then we assume D1 to be on. Let's assume D1 and D2 both to be on. So if both of them are on, then this will be a bit difficult for us to solve. Give me 1 second. Okay, so this would be 1K, this will be 1K, this is short circuited, this will be 1K, this is 1K, right? So this is 10 volt, This is 3 volt. So yeah, so this point potential is 3 volt, right? So if this point potential is 3 volt, I don't know what is the point, what is the potential here. Then let me assume that to be V. So this, okay, if this is V, right, so I can apply a KCL at this particular node, that would be V minus 10 upon 1 plus V uh, minus 3 upon 1 plus V upon 1 equal to 0. So that would be equals to 3V 3V is equals to 13. So your V is equals to 13 by 3. Okay, so V comes out to be 13 by 3. If V is 13 by 3, that is approximately 4.33. 4.33. So it is 4.33. So if it is 4.33, that basically means that current will flow from here to here, correct? Because this point is 3. So current is flowing from P to N for the diode D2, that is fine. What about if, what is the amount of current? That is 4.33 minus 3 by 1, that is basically 4.33 minus 3, that is 1.33 by 1, that is 1.33 milliamps of current. And this current is 3 milliamps amount of current. So this is 1.33 and this is 3. That means from here again some additional current needs to flow, that is 1.67 milliamps. Hence, certainly, what I can say? I can say that your D1 also will be 1, because the assumption was that both are on, and in both the cases I am getting a positive current, hence both of them will be on. Now, what are they asking? They are asking this current only, the current through the diode D1, that is 1.67. So your answer is 1.67. So we got to our answer 1.67. They have asked in milliamperes. So this will be your answer. Let's now solve the next question. This is the next question, right? So here an asymmetrical periodic pulse train Vin of 10 volt amplitude with on time being 1 millisecond and off time being 1 microsecond. So what do they mean by asymmetrical? So on time is 1 millisecond. That is on time. Okay, so let's say it was on initially and this was 10 volt and then it was off always. So that was 1 millisecond. Okay, and then it was only off for a very small fraction of time, that is 1 microsecond. Then on, then again it was on. So basically it is asymmetrical because this square wave, you see, it is not symmetrical. Basically the on and off times are different, correct? That is the reason why it is called asymmetrical. Cool. Now what are they asking? They're telling me that the circuit shown in the figure D1 is ideal. Okay, the difference between the maximum voltage and the minimum voltage of the output voltage VO in integer. Now here so this is 1 millisecond, this width is 1 millisecond, and okay, just hold on, this much amount of width is 1 millisecond, right? And this is 1 microsecond, although this is not up to scale, but I hope you get the point, right? So this is 1 microsecond. Okay, so that's all. Yeah, now the difference between maximum and minimum voltage of the output voltage waveform, right? So if this is like, what is happening, the on period is very higher than the off period, correct? So it will be on for a very large amount of time. So I can approximately assume that this voltage across the capacitor has settled to 10 volt, because the on period is much larger than off period. So approximately I can assume that capacitor has reached the steady state. Approximately I can assume this capacitor has a voltage plus minus 10 volts. Okay. Now it is a asymmetrical periodic pulse train. Asymmetrical periodic pulse train. If it is asymmetrical periodic pulse train, then yeah, this is correct. Now what happens is, when, so I can assume my capacitor has reached steady state to plus 10 volts. Why? Because the on period is so high, right? If this voltage is on almost for all of the period, so then what will happen? It will charge the capacitor, and if it charges the capacitor, I do agree that diode can turn on. That is fine. Diode can turn on. Diode of course will turn on, right? So let me draw the circuit. Yeah, let me copy this circuit. And this would be V in, and I'm just considering the on period, right? When this V in is equals to 10 volt, correct? So if it is on, what will happen? Of course, this point potential is higher, so capacitor will energize and some current will flow like this, and if some current flows like this point potential is higher, so ultimately the P2N voltage across the diode is positive. That means your diode D1 will be turned on, so this will be short circuited, correct? This will be short circuited, so this will just energize the capacitor, and we know, so ultimately your resistor will be short circuited. If it is short circuited, what will happen? Capacitor will instantly get charged to plus 10 volts. It will be instantly charged to plus 10 volts. Okay. Now what is happening? Next, what is happening? When the voltage, input voltage is going to negative. When the input voltage is going to, not negative, sorry, when the input voltage is going to 0, that means this is short circuited. If it is short circuited, this point potential, the capacitor potential is plus minus 10 volt. Capacitor potential is plus minus 10, right? So this point potential is plus, this point potential is minus 10. So diode D1 is turned off, right? Because P2N voltage is negative. So D1 diode is turned off. So only what is happening? Your capacitor is discharging through the resistor. What is the RC time constant here? R into C. It is 20 nano, raised 10 raised to power minus 9 into 500 kilo. So this is almost 10,000, 10 raised to power 4, 10 raised to power minus 6. So this is 10 raised to power 4 microseconds or 10 milliseconds. So your time constant, discharging time constant is much larger than the off period. Your off period is only 1 microsecond. So for only 1 microsecond of time, the capacitor is discharging. So this will almost remain at 10 volts only, almost, right? So what is my V out? What is happening to V out? When input is on, the capacitor is already at 10 volts. Diode is turned on. That means this is short circuited. So your V out is 0. When the input is on, your V out is 0 for 1 millisecond. Okay. Now when your V out is off, correct? When your V out is off, right? Sorry, no, when your input is off, basically 0 volts, then what happens? Then your diode is open circuit, then this point potential, right? Then the potential across the capacitor is equals to my output voltage, right? If I choose this as plus and this as minus, which is minus 10. So it is minus 10, correct? So basically it is negative for certain, it is negative for 1 microsecond, minus 10 for 1 microsecond of time, right? I hope you can apply the KVL here, right? Capacitor voltage approximately is minus 10 only. Yes, it will discharge, but that will be very much negligible. What are they asked? They are asking me the maximum voltage and the minimum voltage of the output voltage waveform. So minimum voltage is 0 and maximum peak voltage is 10. So they are asking me the difference between that. Difference between the maximum voltage and okay. Sorry, minimum voltage is minus 10, right? Minimum voltage is minus 10. Maximum voltage is 0 volt, right? Minimum voltage is minus 10, maximum voltage is 0 volts. So they're asking me the difference of maximum minus minimum. So minus of minus 10, that is 10 volts. So 10 volts will be your answer. So question is pretty simple. This question can be solved in 1 minute only. But I'm explaining you each and everything so that few things are also revised here. Let's solve the next question. So okay, let me mark the numbers here. This would be 8, this would be 9, this would be 10. Okay. So here we have been given the circuit whose characteristics of the diode are shown. The ratio of the minimum to the maximum small signal voltage gain delta V out upon delta V in, right? So yeah, it is delta V out upon delta V in. We have to calculate the ratio of the minimum and maximum small signal voltage gain. Okay, what is the minimum and maximum small signal voltage gain? So when the voltage gain will be minimum and when the voltage gain will be maximum, that is what they want for me to find out. So if you assume that your diode is on, okay, if you assume your diode is on, then this will have a constant potential of 0.7. If you assume your diode to be on, this will have a constant potential of 0.7. Right, 0.7 volts. Now then what are they asking? They're asking me the voltage gain delta V out upon delta V in, right? They're asking me minimum maximum. I'll come to that. Let me first compute the voltage gain. Okay, when it is on and when it is turned off. There are only two certain cases, right? Either it is off or it is on. If it is off, that means the current is 0. That means it is open circuit. It is on, it will be replaced with a voltage of 0.7 volts. That's all, right? So let us compute that. So if I compute this, what will happen? Your V out will be equals to V in into, okay, how do I compute this? So this voltage is 0.7, right? This voltage is 0.7 certainly. So this voltage would be okay. Let me think about this. This voltage is 0.7. So if can I come do something? So this is V out, right? So this point potential is V out, VO. Okay. So this current would be V minus VO by 2, VI minus VO by 2, and this current would be this point potential is what? This point potential is VO plus 0.7, right? So I can apply, what can I do? I can actually, can I apply a KVL over here? Will that help me? That will not actually help me. Okay, I'm just thinking. Okay. So this point is minus plus minus 0.7. I don't know the potential here. Okay, if I assume some current I, so from here some current I is coming, right? And some current Ix is leaving out, and this will be I minus X. Ultimately from here again the same current I will go out. So if I apply a KVL here, let me apply KVL, that would be minus V in plus I into 2 plus 0.7, sorry, this will be minus 0.7. Why? Because across this the potential is minus 0.7, right? Minus 0.7. Then plus 2 into I. Okay, that is equals to 0. Yeah. Now we can actually write what is my I. What is my I? So my I would be 4I would be equals to Vi plus 0.7 by 4. Okay. So this is my I. Now I can compute what is my VO. How? If I apply KVL in this loop, right? So minus VO minus 0.7 plus 2I equals to 0. So VO would be equals to Vi plus 0.7 by 2 minus 0.7. So that is equals to Vi minus 0.7 divided by 2. That's all. So this is what my VO is equals to, right? This is what my VO is equals to. So this is what my VO is equals to. Now, what is small signal voltage? Again, del VO upon del VI. It will be del VO upon del VI. In the case 1, it will be 1 by 2, right? Just differentiate your output voltage with respect to input. It is 1 by 2. Now, what about the case when the diode is off? When the diode is off, it is very simple for us to compute when the diode is off. If the diode is off, that basically means that your output voltage, right, is the voltage here, because this point is shorted. So it will be 4 by 6 into V. That is my VO. So your VO will be equals to 2 by 3 into Vi. So now if I differentiate my VO with respect to Vi, it will be 2 by 3. So what is this? This is the higher value, right? When the diode is off, then the small signal is higher. When the diode is off, then the small signal gain is half. So they are asking me the minimum to maximum. So minimum is half. So 1 by 2 upon the maximum. Maximum is 2 by 3. So it will be 3 by 4, which is equals to 0.75. Okay. So your answer is 0.75. This is your answer for the question. Pretty simple, but bit of thing to think about, because this is not a defined term. Okay, they just defined it so that for this question you will solve it. Okay, it is not like some standard thing that you will remember and memorize. Let's solve this question. In the circuit shown below, D1 and D2 are silicon diodes with cut-in voltages 0.7. We have to plot the V in versus V out, basically the transfer characteristics. So yeah, let's check. So if my V in is very high, okay, let's say 1 volt. If my V in is very high, greater than 1 volt, what will happen? If I assume both of them to be off, so no current is flowing here. So this point potential is 1 volt and this point potential is greater than 1 volt, let's say 2 volt. So certainly D1 will be turned on because it's cutting, like the potential difference is greater than the cut-in voltage. Potential difference is 1 and cutting voltage of this diode D1 is 0.7. So D1 certainly will be turned on, and if D1 is on, certainly D2 will be turned off because it is in the opposite polarity. So there is reverse biasing. Right? D2 is off, D1 is on. Correct? So if D1 is on, that means what is your VO? VO would be equals to, when D1 is on, VO is equals to V in minus 0.7. So what is the slope? It is 1. So we see, if my V in is greater than 0.7, then always certainly D1 will be turned on, and if D1 is turned on, then this will be the curve. So for V in greater than 0.7, I will follow this curve. So basically this will be the curve that will be followed. Okay, for V in greater than, okay, hold on a second, yeah, for V in greater than 0.7, yeah, this will be the curve that will be followed. Okay, now if my V in is less than 0.7, correct, if my V in is less than 0.7, then what will happen? Hold on a second now. So yeah, because if this diode will be turned on and if this diode is on, then certainly hold on a second, no, I'm sorry, extremely sorry, V in greater than 0.7 is not correct. So whenever this diode D1 is on, then always your V out will be this. But when will this diode be on? This diode will be on when the potential difference between this point and this point is 0.7, correct? Now how do I calculate the potential? How do I calculate the potential difference? This has to be greater than 0.7. Okay, just give me 1 second. So yeah, V out, when this diode D1 is on, V out is equals to V in plus 1. Yes, that is correct, but it seems like I'm making some sort of mistake. Okay, this is off. So what is the current? So current is VO minus V in by R. Okay, so yeah, okay, sorry. So what is the current here? Current would be VO minus 1 divided by 1 kilo ohm. That is the current, right? And what is VO? VO is V in minus 0.7 by 1k. So basically what is the current? This I current. This current is VO minus 1 divided by R, and that is the same current as the diode current. And for the diode to be on, like, yes, there are two conditions. One condition is obviously it must, like, the potential difference when it is off, it must be greater than 0.7. That is one condition. But as soon as this diode has been turned on, right, the current must be flowing from P to N, and this diode will be replaced with a 0.7 volts of voltage source because the cut-in voltage is 0.7. So basically this diode is 0.7 volts, and that is the current, right? That is the current, 1 kilo. Okay, so this is my V in, right? So basically what is the current? How do I compute the current? Current is V in, and okay, there is a 1 volt potential as well, right? Current is V in minus of minus 0.7 plus and minus of 1 volt, okay, upon 1 kilo ohm. I hope we can calculate the current in this loop. Very simple. So I will be this. So your I is this, that is V in minus 1.7 divided by 1 kilo ohm. So your I must be positive. I must be greater than 0 if the diode D1 is on. That means your V in Vi must be greater than 1.7. Okay, I was wrong here. Initially I was also thinking in the wrong direction, because I assume that okay, only the voltage needs to be, only there must be potential difference that must be greater than 0.7, then it will turn on. No, I'm wrong, I'm sorry, because you will have to consider whenever the current starts flowing, there is a drop in the resistor. As soon as there is a drop in the resistor, this point potential will be higher. So intuitively, that's why your V out must be, like, your V in must be somewhat greater than 0.7, that is 1.7 in this case. Okay, I hope that makes sense, because there is a drop across the 1 ohm resistor. So whenever my V in is greater than 1.7, this will be on, okay, and the slope will be 1 because my V out will follow this relation. Now as soon as my V in is less than let's say 0, or let's say it is 0, whenever my Vin is 0, what will happen? Oh, certainly this will not turn on. Okay, intuitively I can say this will not turn on, and certainly this will turn on. Again, some current will flow from here to here. Correct? What is the current? When D2 is turned on, what is that value of the current? So ID2 current direction I am showing, that is equals to 1 minus 0.7 upon 1 kilo ohm, right? Okay, not 1 actually, sorry. 1 minus 0.7 minus Vin, right? Because this side I have potential Vin. I assumed it to be 0 volt, but let's assume it to be unknown number, that is Vin. Okay, which is certainly lower value. We'll see that. So this ID2 has to be positive, right? For D2 to be turned on. So that means 0.3 minus Vin must be positive. That means Vin must be less than 0.3. So we got two relations, right? When D2 is on, Vin must be less than 0.3. I see Vin less than 0.3. I don't see Vin less than 0.3 here, right? So when Vin is less than 0.3, what will happen? This D2 will be turned on. Then what will be my Vout? Vout, if you see, will be equals to, Vout will be, if I apply KVL, minus plus, so Vin, Vout, this will be, okay, Vout will be Vin, this is plus minus 0.7, right? This is also plus minus, so minus and plus. So it will be Vin plus 0.7. Okay, so Vout will be Vin plus 0.7. So if I put Vin equals to 0.3, Vin equals to 0.3, what is the value? Vo is 1. So at 0.3 I see Vo is 1. At 0.3 it is 1. Yes, correct. But before 0.3, right? Just before 0.3 it should start reducing. What is the slope? Again, if you see the slope here, slope is again 1. So it should reduce with a slope of 1, which is not happening over here, which is certainly not happening over here, because like this is anyways wrong from the first case, which is happening over here certainly. And after 1.7 the slope is 1, before 1.7 also slope is 1, but at 0.3 I see the voltage is 0, Vout is 0. Is it correct? No, at 0.3 the voltage is 1. So it is certainly not correct, right? So this will be wrong. Okay, so yeah, only option is this one. And again, if you want to verify, you can verify. Let's assume Vi equals to 1 volt. Let's assume Vi is equals to 1 volt. If you assume Vi is equals to 1 volt, okay, if I assume Vi equals to 1 volt, so this point potential is 1 volt, correct? Now you assume both of them to be off, or let's assume Vi to be not 1 volt, let's assume Vi to be 0.9 volt. If you assume both of them to be off, right, then this point potential is what? 1 volt. This point potential is 0.9 volt. Again, which is less than the diode forward cutting voltage, right? Certainly both of them will be off. Anyways, this diode is reverse bias. D1 is reverse bias. D2, yes, it seems like it is forward bias because this point potential is higher than this point if I assume this to be off. But then what happens? But the potential difference is not greater than the cutting voltage. Certainly both of them are off, then my Vout will be equals to 1 volt, right? Because it is off, there is no voltage drop across the 1 kilo ohm resistor. So Vout is 1 kilo ohm. Sorry, Vout is 1 volt. So Vout will be equals to 1 volt when both of them are off. Certainly this is not following the same trajectory. This one certainly is. So option A will be correct, right? There are multiple ways to solve this question. You can solve this in a quicker manner as well, but I just try to give you an intuition. I think in the other marathon we will get a different approach. That also you can see. I just gave you a very basic approach. So let's solve this question 12. So this is the next question. In the circuit shown, n is to 1 step down transformer and diodes are ideal. Both the diodes are ideal. The diodes have no voltage drop in forward bias condition. The diodes have no voltage drop in forward bias condition, so they are ideal. If the input voltage is 10 sin omega t and the average value of the load voltage VL of t in volts is 2.5 by pi. Okay, so this average voltage is 2.5 by pi. What is the value of n? That is what they're asking me, right? So this is nothing but a full wave rectifier, transformer full wave rectifier, correct? This is the circuit of a full wave rectifier with transformer. So do you know what is the average output voltage across a resistor in case of a full wave rectifier? It is Vm by pi. There is a derivation, I will not go into that. Okay, let's assume Vm dash by pi. Whatever is the peak voltage that is applied here, Vm dash by pi, that is the average voltage that comes here. So my Vm dash by pi is equals to given as 2.5 by pi. Okay, so my Vm dash is equals to 2.5 volts. Vm dash is equals to 2.5 volts. Okay, now that Vm dash is the peak voltage that appears here. What is the peak voltage here? 10 volt. So it is a n:1 transformer. The voltage here would be, the peak voltage that would appear here would be 10 by n. So basically my 10 by n is equals to 2.5. So what is my n? N is 4. So 4 would be your answer for your question. Like, I don't think this is much of a fancy question. All you need to know is this is the circuit of a full wave rectifier. Okay, you can go and watch the videos, the explanations, you will see that. Now let's solve this question. This is the next question, question 13, correct? Yeah, question 13, right? So as shown in the circuit, the initial voltage across the capacitor is 10 volt with the switch being open. The switch is now closed at t equal to 0. The total energy dissipated in the ideal Zener diode after the switch is closed is approximately equals to what? What is the total energy dissipated? Okay, that is what they are asking me. Total energy dissipated in the ideal Zener diode. Okay, so how do I calculate the energy dissipated, right? So what energy dissipated would be basically the power, right? So what is the power across the Zener diode? It will be Vz into Iz, and energy would be integration of the power over the given time period. So they are asking me what is the total energy dissipated. So basically if current is flowing after t equal to 0, so energy will be integration of power from 0 to infinity, Iz dz dt. Okay, that is point 1. Point 2 is your Vz is constant. It is an ideal Zener diode. As soon as the current will start to flow, if current flows, the Vz will be 5 volts. So this will be 5 volt. And I will integrate 0 to infinity into Iz of t dt, correct? So yeah, what about your current? What about your what about your current, right? So if I close this switch, if you observe this circuit, it is a C, that is a voltage of 10 volt, right? And I have a resistor over here, and then I have a 5 volt, and this resistor is 10 kilo ohm. Okay, now what will happen? This capacitor will start to discharge at t equal to 0. What is the current? It is 5 by R basically, if I assume 10 kilo ohm to be R. Okay, capacitor is discharging basically, right? Capacitor is discharging. Now it will discharge to what? At steady state, we know capacitor will be open circuit, there will be no current. And when there is no current, when these 2 point potential are same for a resistor. So if this point is potential, when the Zener diode is on, it is 5 volt, this point potential also will be remaining at 5 volt, right? So both of them will be at same potential. So basically your capacitor will reach to 5 volts. At steady state, your capacitor will reach to 5 volts. Okay, so how do I do we even need anything? I don't think we need much of it from here, like we can easily solve it. So all you need is the current equation. What is the current equation? The current equation is 5 by R. R is 10 kilo ohm, so it will be 0.5 milliampere e raised to power minus t upon tau. Tau is R into C. C is given, R is given, right? I can say you what is C. C is 10 microfarad. So it will be minus T by R into C. Okay. So that is your current IC of T. So this is my .5 e raised to power minus T upon RC. Okay. So yeah. So if I replace that, right, because they have asked in millijoules, so I will replace my current in milliamperes. So this will be 5 0 to infinity 2.5 e raised to power minus T upon tau. Now again I can replace by T in milliseconds. It does not matter because infinity milliseconds and infinity seconds are same, and 0 milliseconds and 0 are same. But what is RC? So RC would be, R is 10 kilo ohm, C is 10 micro, right? So if I replace this, okay, let me keep it in micro only. So this will be 100 milliseconds, which won't matter. Okay, but which will matter because I will have to divide as well, right? So yeah, let's keep it in seconds only. So this will be 0.1 seconds. Okay. So this will be T upon tau, that is 0.1 seconds. So this will be 10T. 1 by 0.1 is 10. So into dt. Okay. So this would be equals to this would be equals to 5 into 2.5 divided by 10, that is 1.25. So 1.25, hold on a second, 5 into 2.5, yeah, 5 into 2.5 by 10, yes, 1.25. So 1.25 is your answer for the question, right? If I am not mistaken, hold on a second, this is 0.5, 5 divided by 10, right? Yeah, 0.5. Oh sorry, this is not 2.5, this is 0.5. Oh, I'm sorry, how did I write this 2.5? I'm sorry, this is 0.5, right? Yeah, sorry. So this divided by 5 actually. So yeah, 0.25 millijoule is your answer for the question. So they have asked us to round off to 3 decimal places, so 0.25 only would be your answer. So this will be your answer for the question. Let's now move on to the next question, 13 and then 14. I guess this is the last question. Correct, this is the last question for diode. No, there are a few more questions. So all the diodes in the circuit are ideal, and this is the circuit of a full wave rectifier. And what are they asking? So if some current flows like this, yeah, which of the following plots for Vi is correct? If it is swept from minus M to plus M. So if it is a full wave rectifier, when my voltage is negative, so it is a full wave rectifier, right? So your VO will be simply mod of Vi, that's all. All diodes are ideal, your VO will be simply mod of Vi. It is simply a full wave rectifier. So your VO is mod of Vi. So option A is certainly correct. Okay, option A is certainly correct. And your okay, this was with respect to VO and Vi. Now they are plotting with respect to II, Vi and II. So VO will be mod of Vi. What about your current, input current? So your input current, right? Input current, what will happen to your input current? Okay. So if I see, if this voltage is positive, that means this point potential will be higher. So this diode will be turned on, and this point potential will be lower. Hence this voltage, this diode will be turned on. So current will flow like this. Okay. So the direction of the current when my input is positive, right? According to the reference. Now if my input is negative, that means this point potential is higher. That means this diode will be turned on, and this diode will be turned on. That means what will happen? Current will flow like this through the resistor, which is in the opposite direction. So when my input is negative, current also is negative. So certainly this will be not the graph that I will follow. I will follow this graph. So this first part is pretty simple. it is simply a full wave rectifier. So your output will be mod of input, certainly. But second part, plotting the current with respect to the input current, this you have to understand carefully. Whenever your input is positive, your current is positive. Whenever your input is negative, your current is negative. Okay. So VO is equals to minus of VI is equals to II is equals to when my input is negative, your current also will be negative. That is the bottom line. So option D and A are correct. So let's solve the next question. So this was the 14th, this is the 15th question. So overall we have solved 15 questions from diode circuits. So the diode in the circuit shown below is idle. The input voltage Vi is this. The time duration in milliseconds for which the diode will be forward biased during one period. Okay, diode is idle, so it will be forward biased when the input would be greater than -5. I think that's pretty simple, right? Because this does not have any cutting voltage. So when the diode is turned off, the N has a potential of -5. The P, this has zero current, must also have a potential of greater than -5. That is -5, -4, -3, all of it will work, right? So the point when my Vi is greater than -0.5, for that duration diode will be on. So for what duration the input voltage is greater than -0.5? If I plot my sinusoidal over a graph, Vi, so which is this, right? So minus 0.5 will be lying somewhere here, correct? So my input must be greater than this part, right? So when is the, so it is Vm sin omega t, that is 10 sin omega t. So it varies from +10 to -10. So we have to just calculate this point, right? This duration, if I calculate over a whole period of 2 pi, right? I will convert this into time, don't worry. If I just calculate this particular pulse width t, then if I subtract it from 2 pi, for that whole duration, my input voltage is always greater than 0.5. That is it, right? So let us do that. So what is this value? So this will be basically 10 sin 100 pi t equals to -0.5, correct? So for this I will get two solutions. One will be theta, one will be pi minus theta. So 0.5 divided by 10, okay, which is actually quite large. Yes, so not 0.5, what I am doing? Why is it 0.5? I'm sorry, why am I thinking 0.5? I'm extremely sorry. It is -5. I don't know from where I got the -0.5 number. I don't know. My brain is somewhere else. I'm extremely sorry. Wherever I mentioned 0.5, it should be -5. I'm extremely sorry. It should be -5. So whenever my input potential is greater than -5, then we get to our solution, right? So yeah, so it is basically half. So this right, this will be, I think, 5 pi by 6 or something. Let me just calculate this. So 0.5, actually I 0.5 was in my head that I solved this equation. After solving this equation, sin omega t will be 0.5. That was in my head. Okay, that's why I was processing it wrong. So minus 0.5 sin inverse, that is -30, plus if I do plus 360, that would be 330. So this angle will be 330, right? 330, and this also is like, so if this is pi, right? So after pi by 6, that is 30 degrees, I will again get -5. So I hope you can solve the sinusoids. I don't need to explain how to solve sinusoids. I hope that part you can do. So this will be 210 degrees, that is 30 degrees after 180. So 210, 330. So basically your pulse width, right? This was in degrees. Pulse width is 330 degrees minus 210 degrees, okay, that is equals to 120 degrees. So this is my pulse width in degrees. Now what is my pulse width in time? They want in time, right? So if this is in degrees, okay, I will convert this first into radians. So basically I know 180 degrees is pi radians. So 120 degrees would be 2 pi by 3 radians. So I converted this into radians. Now I know my radians. How do I convert this into time? So I know that 2 pi completes a whole cycle. What is a cycle? That is the time period. What is the time period? Time period would be, so what is omega t? So 100 pi is my omega. Omega is 2 pi by t. So your t would be 1 by 50. Okay, t is 1 by 50. So 2 pi covers one time period, that is 1 by 50 seconds. So 2 pi by 3 would cover how many seconds? 1 by 150 seconds. Now they have asked in milliseconds. If they have asked in milliseconds, so I will multiply this by 1000, I will get my answer in milliseconds. So this will be 1000 divided by 150. So 6.67 milliseconds. Okay, so 6.67 milliseconds would be your answer for this question. So you must know how to convert angle, degrees, all these things, right? Okay, just one small thing. If I am dividing if 2 pi is 1 by 50, right? Yeah, 2 pi by 3 would be 2 pi by 3, that is correct. 60, 16 to 2 by 3, yes, that is correct. 2 pi is 1 by 50, right? So 2 pi by t, 50, pi is cancelled, so t is 1 by 50, t is 1 by 50 milliseconds. Your pulse width, okay, I'm sorry, just a so your pulse width is this, right? Pulse width is this. Okay, now actually I told you that our voltage will be always greater than -5 for 2 pi minus the pulse width in radians, or in degrees if you want to say 360 minus the pulse width. Sorry, I'm extremely sorry, just a small error. 360 minus the pulse width. So your pulse width is 120, in pi it is 2 pi by 3. So for what duration the input voltage is greater than -5? It is 2 pi minus 2 pi by 3 in radians. So 2 pi minus 2 pi by 3 in radians, that is 4 pi by 3. So actually your voltage is greater than -5 for the duration 4 pi by 3. So here this will be 4 pi by 3 and not 2 pi by 3. Okay, just a small error. So this will be yeah, 2 pi is this. So this will be 2 by 150. This will be 13.33. milliseconds. Okay, that will be your time check. Sorry, that will be the duration for which your input voltage will be greater than -5 volts, and when my input voltage is greater than -5 volts, of course we know that the diode will be turned on, and that is what they are asking, right? So this will be your answer for the question. Now we will move on to the MOSFETs. So let's begin with MOSFETs. So first we will solve for EE, then we will solve for EC branch. So this is the first question. A common source amplifier with drain resistance RD as this, right? So how do I do you know what is the circuit diagram of a common source amplifier? So common source meaning that hold on, let me draw this VDD, and this is my source, right? Common source basically means where the between the output and the input the source terminal is common. Okay, that is what common source means. And this is my VO and this is my VI, and the drain resistance is this one, and that is given as 4.7 kilo ohm, is powered using a 10 volt power supply. Basically the VDD is 10 volts. VDD is 10 volts. Okay. Uh, Assuming the transconductance GM is 520 microampere per volt, the voltage gain of the amplifier is close to what? Okay, how do I compute the voltage gain? So if the GM is 520, whatever is the GM, let's assume that the GM is GM, right? How do I compute the voltage gain, small signal voltage gain, V over Vi? So if we draw the small signal model, right, then we know the MOSFET will take a current of GM into small signal VGS. So input is Vi, like the gate voltage is small signal Vi, the source voltage is constant to 0. So basically the MOSFET is taking a current of GM Vi. I am just drawing this in rough, but I hope these points you already know if you have studied analog electronics. So it is taking a current of GM Vi, right? And in small signal model, we simply short our supply. We nullify the voltage source and the current source. If I want to nullify my voltage source, I will make it 0. That is, I will short it, Vs equal to 0. If I want to nullify my current source, I will make current 0. That is, it will be open circuit. So basically, your gain would be, what is the current that is coming here? That is 0 minus VO divided by 4.7 kilo, right? And the outgoing current is what? It is simply GMVI, because the MOSFET does not have any output resistance. Ideal MOSFET, nothing is mentioned. So simply your gain would be minus GM into 4.7 kilo into 4.7 kilo basically, right? If your GM is in milli, then kilo and milli will be cancelled. Ultimately it will be GM into RD, right? So there is this formula, that is the formula of a common source amplifier. If you want to remember it's good, but you can derive it. It will hardly take you 30 seconds to derive it. Okay, so yeah, so let me write GM in milliamperes per volt. So GM in milliampere would be 0.52. GM in milliampere would be 0.52 milliampere per volt, right? So what is your voltage gain? AV is equals to minus 0.52 into RT, that is 4.7. So this would be, if I solve this, 0.52 into 4.7, so that is minus 2.44, right? So 2.44 is present in option A. So option A would be your answer. Like this is like a 10-second question if you directly use the formula, but we want to derive it as well, so that's why. This is the second question. The cross section of a metal oxide semiconductor structure is shown schematically, starting from an uncharged bias of 3 volt applied at the gate contact with respect to the body contact. So with respect to the gate, I am applying a potential of 3 volt. Okay, cool. The charge inside the silicon dioxide is then measured to be plus Q. So it has a plus Q amount of charge. The total charge contained, okay, Google Gemini suddenly listened to me and it turned on. Sorry about that. It's listened charge and it turned on. Okay, yeah. The total charge contained within the dashed box shown upon the application of this bias expressed as a multiple of Q. Basically, they're asking me the absolute value in coulombs. Okay. So if this is my system, right, and if I'm applying a bias due to which the silicon dioxide is getting a plus Q amount of charge, it will generate a minus Q amount of charge, because ultimately, if it is a dash box, right, and we know the net charge is 0 if this is my only system. So charge can never be generated by its own. So if a positive charge is generated plus Q, same negative charge also will be generated, considering a whole system. So overall the net charge will be same, that is 0, because this is my whole system. So actually they are asking me what is the net charge present in the dash box, that is actually equals to 0. So basically your answer is, it is 0 times q, so your answer is 0. Okay, that's how simple it is. Question seems very difficult, but actually it is 0, because there is no additional charge here, right? Whatever charge is generated, it will be subtracted, so that will be 0. 0 would be your answer. Pretty conceptual question, like not difficult but conceptual. Let's solve this question. For an ideal MOSFET biased in saturation, the magnitude of the small signal current gain for a common drain amplifier. So this is my MOSFET, it is properly biased, right? And they are asking common drain amplifier, what is the current gain, right? So common drain basically means this part is common, right? And in common drain, your input is the gate and your source is the output. So what is the input current? Your input current will always be 0. Ig input current can never be equals to something greater than 0, although it is some small amount of current, we do know it, but approximately it is 0, and your Is current will be some finite current. Okay, so your current gain actually is infinity. Okay, your current gain is infinity because your Ig is 0 due to the silicon dioxide. We know gate current is always 0, so you are getting a finite current upon 0 current, that is your current gain. So your Ig is very small, so it is tending to 0, so your current gain would be tending towards plus infinity. Okay, so that would be D. That would be D actually. So let's solve this question. This is the next question. Which one of the following statements is true about the small signal voltage gain of a MOSFET based single stage amplifier? Common source and common drain are both inverting amplifiers. So if I draw the MOSFET, so in double E, right, whatever questions come from MOSFET, they are like cakewalk, very simple, very easy, they are not that difficult. Okay, so this is my gate, this is my source, and this is my drain, right? And they're telling me that common source and common gate amplifiers both have inverting, both are inverting in nature. So we certainly know that common source is certainly inverting, because we know if I'm moving from gate to drain, we get a phase shift of 180. Why? Because if you remember in the gain formula, it was minus GMRT, so there was a negative phase shift. In all other cases, right, if I go from gate to source, there will be 0 degree of phase shift. If I go from drain to source, right, if it's a common gate amplifier, then also there is a phase shift of 0 degrees. There is no phase shift. Only if I move from gate to drain, then only there is a phase shift of 180. So common gate amplifier does not have any phase shift of does not have any phase shift. Okay, from drain to source, we don't have any phase shift. Can you verify it? Yes, we can. So if it's a common gate amplifier, right, this part is common, and we're applying a voltage here. So let's assume that if I this voltage is some DC biasing voltage, right? So this will be sorted. If it's a common gate amplifier, we apply a biasing voltage at gate, that's all, to bias the transistor, that's all, right? So if it's a DC voltage in small signal AC analysis, I can short it. Now if I short it, what will happen? If I short it, this will be 0. Let's assume that this voltage is some Vs, right? So and if I assume that there is some resistor connected here, RD, right, and then there is some supply, and I can short it again because it is a DC supply, it can be shorted. So what is the current? Current is GM into VG minus VS. VG is 0 because it is shorted, minus VS, it is VS only. That is equals to this current, right? That is equals to this current. What is this current? That is equals to 0 minus VD, that is my input or output. I exactly don't remember why do we take the output, I forgot. Okay, so 0 minus VD divided by RD. So what is happening? If you see your Vs over VD or VD over Vs, you see it is coming out to be, if I say VD over, so that gives a good expression. Actually we take the output always from drain, right? So VD over Vs is coming out to be plus GMRD. So it is positive, there is no negative sign. So there is no phase shift. There is 0 degrees of phase shift here, right? There is 0 degrees of phase shift. Okay. So yeah, that's all. That's all basically. There is 0 degrees of phase shift and we don't get any phase shift. But they're telling me it is inverting. Inverting basically means we get a phase shift. No, that is wrong. Common source and common gate amplifiers both are non-inverting. No, common source amplifier is inverting. Common source is inverting. Common gate is non-inverting. Absolutely correct. Common source is non-inverting, common gate is inverting, they are telling the opposite. So certainly option C will be the correct answer for this question. Let's solve the next question. This is the next question. That is the last question that came in gate EE. In the circuit, IDC is the ideal current source. The transistors M1 and M2 are assumed to be biased in saturation. So both of them are in the saturation region, wherein Vin is the small signal input voltage, VDC is some fixed bias voltage. Both transistors have small signal resistance, output resistance, drain to source, that is RDS, and transconductance of GM, the small signal output impedance of the circuit. So basically they are asking me what is the output impedance Z out from here. If I want to compare the output impedance, IDC is a bias DC current, right? So this will be open circuited. So this will be open circuited. I can replace my MOSFET with its own small signal model. So this VDC will be shorted. If this VDC is shorted, let's assume that this potential is Vx. If I assume this potential is Vx, then what will be this current? This current will be 0 minus Vx into Gm of the transistor. Both of them have same Gm. So there will be a current that will flow, that will be equals to what? Minus Gm Vx, right? So this current is minus Gm Vx, and of course I have a, from drain to source there is a current, from drain to source there is a output resistance as well, that is RDS. Now again similarly if I see here, of course Vi will not be shorted, this is shorted. So what is the current? That is GMVI. GMVI is the current here, and you will have a resistance RDS, and this point potential is your Vx and this is grounded, correct? And I have to compute the output impedance, that is nothing but, let's say this is V out and this current is I out, right? So I simply have to compute the ratio of V out over I out, that will give me the output impedance. Okay, so yes, you can remember all these things, you can do few things, but I don't want to do it. I want to calculate it with basics. You can remember few things that if it's a diode connected, then what will happen, what will be the resistance, but I don't want to remember anything. I directly want to solve it with basics, right? Okay, so we can apply a KCL at this node. So if I apply a KCL at this node, that will be Vx by RDS plus Vx minus Vo by RDS plus GMVI, and this current is incoming here, right? So this will be minus of minus GMVI, because the current is not GMVI, sorry, GMVx, right? This current is already negative, but it is an incoming current, so that's why there will be a negative sign here, right? Yeah, these are the four things. Okay, so I think I can iron out my Vx and that will help me out really well. Yes, so basically, right, I will need the help. Yeah, I will need the current. One thing is certain, that whatever current is incoming here, IO, right, that will be divided. Again, this current will be IO only, right? This current will be IO only, right? Whatever current enters a node, same current will be exiting from the network if this is a network. So if this current is IO, correct, and this current is GMVI, what will be this current? This current will be IO minus GMVI. So my Vx actually is equals to this current into RDS, that is my Vx. So my network is simplified very much. I don't need to do all this, right? This is very difficult. So I was able to form a shortcut. So I got my Vx, correct? Now you apply KCL here. Now it will be very simple. So your IO will be equals to G minus GM into Vx, right? That is this direction. So minus GM into Vx. Vx is this value, right? I will copy and paste this Vx value. Then it is yeah, it is VO minus Vx divided by RDS. VO minus Vx plus VO minus Vx. Vx is this value. So VO minus Vx divided by RDS. So yeah, IO is equals to minus GM. Okay, let me minus GM RDS into IO plus GM square VI into RDS plus VO by RDS minus IO plus GMVI. Okay. Oh, sorry. Sorry. We are computing the output impedance, right? So if I am computing the output impedance, this current will be 0. Then the circuit becomes so simplified. What am I doing? So the input also will be shorted because we are only concerned about the output impedance. So Vi will be 0. So this current source will take 0 current. So there will be no current here, right? So this GMVI is 0 simply. So basically, right, this becomes IO into RDS. Okay. So this is IO into RDS. So yeah, sorry about that. So Vi is, this is 0. So our calculation will be much simpler. I'm sorry, what am I doing? I'm also in some other loop. Okay. Yeah. Yes, this will be IO. Yeah, this here will not be any GM square term. This will be minus GM RDS IO. This will be VO by RDS and this will be IO only. Yeah. So what will happen? This will be 2 plus GM RDS into IO VO by RDS. So VO by IO, that is what I have to calculate. VO by IO would be equals to 2 RDS plus GM RDS square. Okay. 2 RDS plus GM RDS square, that is present in option C. So your answer would be option C. Okay. Bit calculative, but you can, so it became very simpler when your Vi became 0. Okay. So I forgot, I also forgot that when you are calculating your output impedance, of course your DC sources will always be 0 anyways if you are doing small signal analysis, and if you are calculating the output impedance, of course your input also will be 0, input source also will be 0, right? So if I were to do that, then the calculation became this much simpler. So your answer is this, option C. Now let's start to solve the EC questions. Yeah, this is the first question. The circuit shown in the figure, the transistors M1 and M2 are operating in saturation. So both of them are in saturation, having channel length modulation to be non-zero. Okay, if they are non-zero, then they will have their output resistance RO2 and RO1 being finite. They will not be infinite. The transconductance of the MOSFET M1 and M2 are GM1 and GM2, and of course the internal resistance will be there RO1 and RO2 because they have non-zero channel length modulation. Now they are asking me, ignoring the body effect, what is the small signal voltage gain V out upon V in? So we have to calculate the small signal voltage gain. Let's break down the circuit. For computing the small signal voltage gain, of course, I will short the DC bias sources, and the MOSFET will take. So what is the, so this is a PMOS, this is a PMOS, right? So for a PMOS, this is the source and this is the gate, and the current would be GM VSG. That is how we calculate the current, source current of a PMOS. What is GM VSG? It is minus V in, right? Because source voltage is 0, gate voltage is V in. So 0 minus V in is minus V in. So this will be, this current will be coming as GM minus GM V in, VI. And of course, it has a parallel resistance connected. Okay. I'm just not drawing the current, but I hope you can understand this is a current source, not drawing the current source exactly, but I hope you get the point, right? This is not short circuit, okay? Not short circuit. And okay, let me draw the current source only. And here we have a, again, so what is the, this is again a PMOS, right? So it will not be zero current, you will not find the VGS, you will find the VSG. What is the VSG here? It is this source voltage is V out and gate voltage is 0. So it will be GM V out. That is the current that is outgoing. And of course, again in parallel, it will have a resistance R01. This will be GM1, this will be GM2. Now they are asking me the ratio of small signal voltage gain V out over V in. So yeah, let us, this is V out, right? So we can apply a KCL at this node. So if I apply a KCL at this node, V out over R02 V out over R02 plus V out over R1 plus okay, now here the current is 0, right? And this is a incoming current, so it is minus of, I write my incoming current as negative, minus of minus GM2 VI plus the outgoing current is GM1 VO. That is equals to 0. Okay, so yeah, now let's solve it. So this would be VO 1 by R02 plus 1 by R01 plus GM1 equals to minus of GM2 VI, correct? So what is this basically? If I rewrite this, I can write as 1 divided by 1 by GM1. Okay, so what I can write is 1 by R equivalent is equals to 1 by R02 plus 1 by R01 plus 1 by GM1, 1 by 1 by GM1. So essentially what you are telling me that your R equivalent is nothing but R02 parallel with R1 parallel with 1 by GM1, that's all. And that is what is present in the options. So your VO over VI, small signal gain, is basically minus GM2 over okay, yeah, this is 1 by R equivalent. So this value is equals to what? R equivalent is this, right? So this is equals to what? This is equals to 1 by R equivalent, right? That is equals to 1 by R02 parallel with R01 parallel with 1 by GM1. So this R equivalent can go on the other side, so it will be multiplied, not divided. So this will be R02 parallel with R01 parallel with 1 by GM1. So this is your small signal voltage gain that is present in option C. So certainly your answer would be option C. This is the correct answer for your question. Okay, great. Yeah, I hope I have done everything correctly. I'm just checking whether everything is fine or not. 1/2 R1. Yes, everything is correct. Yeah. Hold on a second. Hold on a second. So GM. Sorry, GM2 should be at the start. Sorry, option D. Option D is correct, right? Because GM2, it should be minus GM2 into 1 by GM1 parallel with R02, R1 parallel with R02. Cool. Yes. So option D would be the correct answer in this case. Let's solve the next question. That is this one. Right. So again a gate EC 2021 question for the transistor M1 shown. Its mu and COX value is given. WL value is also given. All these are given. The channel length modulation coefficient is ignored. So lambda is equals to 0. The gate to source voltage VGS is 1 volt. It is talking about the biased voltage, right? To keep the transistor at the edge of the saturation. Then the threshold voltage of the transistor would be. Do you know when my transistor is at the edge of saturation? That basically means the drain current, if it is at edge of saturation, right? That means it is going from linear region to saturation region. If it is at edge of saturation, because if you remember the graph of ID versus VDS, right? So at when the VDS is 0, then it is at linear region, correct? If for VGS greater than VT, for VGS greater than VT, right? Initially it is at linear, then only we move on to saturation region where my current ID does not depend on the drain to source voltage anymore. It depends on the gate to source voltage only. That's why it behaves somewhat constant. Okay, all these are there. So if it is at edge of saturation, that basically means for this particular value of VGS, the drain current in linear region and the drain current in saturation region both will be equal. So ID sat will be equals to ID linear, right? So what is ID saturation? ID saturation, right? ID saturation would be mu1 COX into W by L into W by 2L. Okay, this is a saturation current. W by 12 into VGS minus VT whole square. Right, this is the expression for saturation current. What is the expression for linear current? It is mu n COX W by L. There is no two term into this would be equals to VGS minus VT into VDS, right? Approximately. If lambda is there, then this becomes then we have, what do you call, then we have uh, the VDS square by 2 term as well, right? Yeah, this is one way to go about it. Another way to go about it would be like there are too many variables over here. Yeah, VGS I know, VT I know, CX, WL, everything I know. I can compute the VDS from here. If I compute the VDS, will that help me? No, that will not help me. Okay, already VT is unknown to me, right? So solving this equation would be a bit tedious to me, right? Solving this equation would be a bit tedious for me. So what we can say is we can actually say this, if it is at edge of saturation. So do you know what is the condition for the MOSFET to be in linear region? Basically my drain to source voltage must be less than or equals to my VGS minus VT, okay, right? And my gate to source voltage must be greater than or equals to, sorry, my drain to source voltage must be greater than or equals to VGS minus VT if it is in saturation region, right? So on the edge of the saturation, these two conditions must be equal. So basically, you at edge of the saturation, your VDS must be equals to VGS minus VT, right? That can be observed from here as well. Yeah, I think you, so you will have to write here VDS square by 2. That is also in the formula. If you don't write VDS square by 2, then this formula will not be valid. Okay, so yeah, don't forget there is VDS square by 2. If VDS is very small, then we assume that basically this is 0. That's why we make this approximately linear. So that's why it follows linear initially when the VDS is very small. Okay, that was the reason I also forgot to write it. Okay, for approximated value this is correct, but when VDS is very high, right, then you will have to write the whole formula. Okay, but we don't want to use this formula, we can use this condition. So what is my VGS? VGS is 1. I don't know what is my VT, right, but I certainly know my VDS will be equals to 1 minus VT. Okay, why will it help me? Because if I know the drain to source voltage, I know the voltage at this point, and I can compute the current with that information. So what is the current? Current is VDD minus VDS divided by 20 kilo. So VDD is 3 volts. So 3 minus VGS. Sorry, 3 minus VDS. VDS is 1 minus VT divided by 20 kilo. 20 kilo ohm, right? 20 kilo. That is equals to my ID, and this ID will be satisfying this particular equation, VGS minus VT, right? Or I can directly write this as VDS only, right? VDS is equals to VGS minus VT. So directly I can write this as VDS. So basically this will be, let's assume VDS to be some voltage Vx. So this is Vx, that is equals to mu n COX W by 12. So mu n COX is given as 100 micro ampere. Let me convert this into milli. Why? Because this 20 is in kilo, right? And if this is in volts, so I will get milliamps of current. So let me write this in terms of milli. So mu n COX, that is equals to 0.1 milli, 0.1 milliampere by voltage square into W by L, that is 10, divided by 2, right? W by L, 2L, and yeah, mobility, COX is the offset per unit capacitance, W is the width, right, into Vx basically whole square, right? That is the current equation. So now let's solve for Vx, correct? So we can write this kilo as 20 only because this is milliamperes, this is also milliamperes, so ultimately the units will be cancelled, no need to worry. So this 2 can, this will be 1, this 2 can be 10. So ultimately the equation is Vx square plus 0.1 Vx plus 0.1 Vx, and this will be minus 0.3 equals to 0. Okay, so yeah, that's all. And yeah, minus, so your answer would be minus b plus minus b square, that is 0.1 whole square, minus 4ac, so this will be plus 1.2 divided by 2a. So yeah, this would be, if I solve for this, I think it will be almost 1.2. So of course ignoring the negative solution, because VDS cannot be negative, VDS has to be positive, right? So 0.1 square plus 1.2 whole under root is 1.1. Of course ignoring the negative solution, choosing the positive solution, right? So if I ignore the negative solution, because that will give me my negative VDS, that is not possible. For NMOS, VDS cannot be negative if it is in saturation. So choosing the positive solution, Vx would be equals to 1. Okay, because this will come out to be 1.1. So 1.1 minus 0.1 is 1 divided by 2. Sorry, VDS will come out to be 1 divided by 2, 0.5. Okay, so it is 0.5. So if your VDS is 0.5, that is equals to 1 minus VT, correct? So your VT is equals to 0.5. That is your answer. VT is equals to 0.5. That is your answer of the question. Pretty good, beautiful question, bit of equations, bit of basics of MOSFETs. Let's solve this question, right? So considering the CMOS circuit shown, the gate width is W by L ratio is given for the following respective MOSFETs. Both the transistors have same gate oxide capacitance. Okay, both the MOSFETs have same gate oxide capacitance per unit area. Same oxide capacitance per unit area, basically their COX is same. That is what they are telling us, right? Is it same oxide capacitance per unit area? Just their COX is same. Yeah, same oxide capacitance per area, their COX is same. Okay, and for the PMOS, the threshold voltage is -1. So threshold voltage for PMOS is -1, right? Okay, and don't worry, if you worry about how is this -1, the formula that we use, in that we use mod of VTP, so it won't stress you. Okay, don't worry about that. The mobility of holes is 40 centimeter square per volt second. So basically mu p, right? Mu p is 40 centimeter square per volt second. Okay, for the NMOS, the threshold voltage VTN is 1 volt, and your electron mobility of electrons is 300 centimeter volt second. Okay, the steady state output voltage VO would be equals to what? Okay, what will be the steady state output voltage VO? So it is like a CMOS circuit, there is no RD essentially. So basically they are in series, effectively they are in series, right? So I will assume both of them to be in saturation. Okay, you will have to assume it, right? If I assume both of them to be in saturation, what are they asking? The steady state output voltage. What will be the steady state output voltage? Okay, so it is not like they are asking me, yeah, they are asking me the DC steady state voltage. So yeah, let's not comment about saturation. Let's try to solve for the steady state output voltage. Okay, so if you assume your VO to be equals to 0, if you assume this to be equal to 0, that means your NMOS is off, because your VGS is less than your threshold voltage. So if your NMOS is off, this part is also off, correct? That should happen technically. Let's see if that happens or not. So if this is 0 volt, right, that means this is 0 volt, this is 4 volt. So your VSG is greater than mod of VTP. Okay, just consider the mod. Your VSG is greater than mod of VTP, so it will turn on, and if it turns on, then certainly it will try to pull it up, right? This voltage will be pulled up. It will not be 0. It will certainly be not 0. There will be some upward voltage. Okay, that will not happen. So it will certainly not be 0. Certainly not be 0. Okay, for the other options, equal to 2, less than 2, more than 2, we will have to solve the question. Okay. Okay. So if it is equal to 2, right? If it is equal to 2, what happens if it is equal to 2? If it is equal to 2 here, that means what is the VDS? The VDS that I see from here, right? VDS would be 2 volt, and it is a diode connected MOSFET. It's a diode connected MOSFET, so it will always be in saturation. If the VGS is greater than VT, it will always be in saturation, right? Diode connected MOSFET, then this VDS greater than VGS minus VT always will be satisfied, right? So this bottom MOSFET always will be in saturation no matter what. Okay, this MOSFET always will be in saturation. Okay, this MOSFET always will be in saturation. Good to know, right? So bottom MOSFET is in saturation. So what is the current equation for the bottom MOSFET? ID would be equals to mu n Cux into W by 12, W by 12 into VGS minus VT. VGS is VO basically. VO minus VT is VT is 1 volt, right? Yeah. VO minus 1 volt whole square. That's all. ID is equals to mu 1 Cx W by L VO minus 1 volt whole square. Okay. Now, for this MOSFET to be in saturation, what needs to happen? Its VSD must be greater than VSG minus mod of VTP. Right? This needs to happen for this MOSFET to be in saturation. Correct? Let's see if that. So, what is the exact condition basically? Then we can comment. So, what is VSD? VSD is VSD. VSD is, so source voltage for this MOSFET is VO, right? So VO minus VD, right? Drain voltage. Drain voltage is 4 volt. So VO minus 4 is greater than VSG. VSG is again VSG is this VS is VO, and okay, VSG is simply, sorry, hold on. VS is 4 volt and gate voltage is VO, right? So this will be 4 minus VO. Okay, because okay, oh sorry, this is also okay, sorry, this is also directly connected, right? Because drain is connected. Yeah, then this also will be always in saturation. This also always will be in saturation. I'm sorry, what am I doing? I'm also in some other area. So mod of VTP is 1. So yeah, your VO has to be just give me 1 second, right? VS, what am I doing? The source voltage here is 4 volt. What am I doing? This is 4 minus VO, right? So this will always be satisfied basically. So yeah, this is your VSD, right? And this is your VSG minus VTP. So this particular thing will always be greater than VSG minus VTP. So this also will be always in saturation. I'm sorry, I missed this point. This also will be always in saturation, right? Now, if this is always in saturation, then you can use the simple current equation. This was the current equation of the NMOS. What is the current equation of the PMOS? The current equation of the PMOS would be nu P COP W. Now W by L are different, right? So here W by L is 5. So let me write this W by L actually in a different fashion so that you can understand it better. So this will be W by L N, and yeah, this will be W by L P, okay, into yeah, IDP, and this would be VO, okay, VSG, right? What is VSG? VSG is 4 minus VO, 4 minus VO minus 1 mod of VTP whole square. So these two currents must be equal. So let me put the coefficients into action. So electromobility for mu1 is 300 and COX is same for both of them. So what will happen? COX will be cancelled and mu1 is 300 by 2 also will be cancelled. W by L in the NMOS is 1, that multiplied by VO minus 1 whole square, that is equals to your mu P. Mu P is mu P is 40. Yeah, mu P is 40 into W by L, that is basically 4. This is not 4, this is 5. This is 5 into VO minus 1 whole square, correct? So not VO minus whole square, so 3 minus 1, 3 minus VO whole square, okay. Okay, so we got to this value. Yep. So now all they want is some they don't want exact number. So if it is exactly equal to 2, what will happen? Will it be exactly equal to 2? No. If I put VO equals to 2, this will be 1 square, this also will be 1 square. So this is saying 300 is equals to 200. That is not possible. So VO certainly will not be equals to 2. Certainly VO will not be equals to 2, right? It can be the less than 2 or more than 2. So let's choose any number, right? Let's choose it to be more than 2. So if it is more than 2, let's choose 2.5. If it is 2.5, this will be 1.5 whole square, that is 2.25. This number is already large, right? And if I choose 2.5, this will be 0.5. 0.5 whole square is 0.25. So what is happening? This number is 200, right? So 200 is already smaller than 300, and I am multiplying a smaller number here. So this will become more smaller and this will become more larger. So the difference will be more. If I choose a number VO that is greater than 2, the difference will be larger. So certainly your VO will be less than 2. Certainly your VO will be less than 2. Okay. How can you verify? Solve this equation. You will get to the answer. So if you choose a VO to be less than 2, let's choose a number that is 1.5. Now, if I choose 1.5, then this will be 1.5 minus 1, that is 0.5. 0.5 whole square would be 0.25. And here this will be 1.5, this will be 1.5 whole square, that is 2.25. So now what is happening? This number is smaller, 200, right? I am multiplying a bigger number. This number is already larger, but I am multiplying a smaller number. So there will be some equilibrium somewhere where these two things will be equal, right? So that's why your VO will be less than 2. Like, although this question is very simple, but I made it a bit lengthy because I was thinking, okay, this is direct connected. It took me a while to figure out this question, but I'm solving this question directly in front of you. It's not like I'm solving this. I have already solved this and I'm just solving I've done the solution. I'm just seeing the solution and solving like by just watching the solution. No, I'm solving this on the open directly. Let's move on to the next question. This is the next question, right? So here the ideal long channel N MOSFET and P MOSFET devices are shown in the circuits, have threshold voltages 1 volt and minus 1 volt. So PMOS has a threshold voltage of minus 1. So VTP has a threshold voltage of minus 1 volt and VTN has a threshold voltage of 1 volt. Okay. The MOSFET substrates are connected to their respective sources, as you can see. For applied voltages as shown, the steady state voltages would be, okay, what are the steady state voltages? So if we assume initially the capacitor are uncharged, so for a NMOS, the higher potential is always the drain terminal and the lower potential is always for a NMOS, the lower potential will always act as the source terminal, and for a PMOS, the higher potential will always act as the source terminal, right? So here what is happening is this is working as my source and this is working as my drain, right? So what is happening? This is at 0. So VDS is 5 volts. VDS is 5 volt currently at t equal to 0. And what is your VGS? VGS is also 5 volts and threshold voltage is 1. So VGS is greater than 1 volt. Yeah, sorry for the interruption. There was noise coming outside, so I had to pause the video. Yeah, what I was saying is, so initially this voltage is 0 and your VGS is greater than 1 volt. So certainly this will be in saturation and slowly current will flow, right, from drain to source, and due to which the capacitor voltage will increase, and it will increase till what point? So your drain voltage is always fixed at 5 volts, right, and your gate voltage is also always fixed at 5 volts, correct? So will this be always in saturation? Let's check that. So what is your VDS? So your VDS, so your VD is equals to your VG, that is certain, right? Your VD is equals to your VG because drain voltage and gate voltage both are same. So your VGS must be greater than VGS minus VT, right? I can, as the source voltage is constant, I can cancel it. So your VD must be greater than VG minus VT, and it is, right, because your VD and VG both are same, that is 5 volt, and your VT is 1 volt. Certainly your drain voltage will always be greater than VG minus VT, that is certain. So your MOSFET NMOS will always be in saturation. So current will always keep on flowing like this, and it will charge the capacitor till what point? So your NMOS, there is one more condition for the MOSFET to be in saturation, that is VGS greater than VT. So basically what is happening, your source voltage is increasing, your VG minus Vs is greater than 1 volt, your source voltage is always increasing, right? If your source voltage is always increasing, this difference will reduce, right? Because Vg is constant, that is 5. So what is the maximum value of source voltage that we can go? Maximum value of source voltage will be 4 volt. If I take my Vs to 4 volt, my Vg is 5, 5 minus 4 is 1. So at that point of time, both of them will be equal. If my Vs is higher than 4 volts, then this will be less than 1 volt, and your VGS will not be greater than threshold voltage, it will be less than. So automatically your MOSFET will turn off. So at Vs equals to 4 volt, MOSFET will turn off. Okay. Now similar analysis you can do here. In case of PMOS, your V1 is 4 volt at steady state. Now in this case what will happen? In this case what will happen? Your VSG, right? VSG, right? Vs is this, G is this, again source is the higher potential. So your source is the higher potential, right? Okay, VSG. Here gate voltage is negative. If gate voltage is negative, what will happen? So basically for the MOSFET to be in saturation, what needs to happen? Your VSG must be greater than mod of VTP. Okay. So your source voltage is the higher voltage, that is 5 volt. This minus VSG, that is 10 volt, must be greater than mod of VTP, which is always true. So this will always be in, okay, this will always be in saturation, right? Okay, and your, because hold on a second, VSG, right? GS VSG. Okay, and what about the other condition, that is your VSD must be greater than VSG minus mod of VTP. So what is your VSD, right? If I see VSD is the source to drain voltage. So it is 5 minus VD. Okay, certainly it is 5 minus VD, and that has to be greater than VSG. VSG we have just computed, it is 10, right? VSG is 10. 5 minus of minus 5, that is 10. So 10 minus mod of VTP, that is 1. So your VD actually has to be less than 9. 9 will go on that side. So this will be minus 4. So VD, right? The lowest voltage, VD has to be less than minus 4 for it to be in saturation, right? And at T equal to 0, the voltage is 0 volt, right? So it is certainly not in saturation. So what is happening? It is, so this is always true, right? So what will happen? Some current will flow from source to drain. In case of PMOS, current flows from source to drain. So if this is greater than 0, right? So if this condition is true, either it is in linear or in saturation. I just confirm that if VD initially at T equal to 0, there is no potential. So this is at 0 volt. So certainly it cannot be in saturation because this condition is not satisfying. VD has to be less than minus 0.4, less than minus 4, but currently VD is 0. So certainly it is in linear. If it is in linear, some current is flowing, that is charging this capacitor. So this voltage is only increasing. It is never reducing, right? For it to be in saturation, my VD must be less than minus 4, right? But it is never happening. Current is flowing from source to drain. Current is only increasing and increasing. Voltage is only increasing. So this potential is going up. What is happening? Your VSD, because Vs is fixed, is going down. So your current ID is also going down. It is going towards 0 because if it is in linear region, we know that your ID is proportional to VSD for small values of VSD. Your ID is proportional to VSD for small values of VSD, right? So that is what is happening. So At steady state, current will be 0 when Vs will be equals to Vd and it will be in linear region. So your V2 will be equals to 5 volt. Okay, so like this you can do. There is a shortcut as well. So your PMOS is a pass transistor logic. If your PMOS voltage is low, then it will pass the whole voltage. If your PMOS voltage is high, it will not pass the whole voltage. That's how you can remember it, right? If your NMOS is high, it will not pass the whole voltage. If your NMOS is low, it will pass the whole. Sorry, if your NMOS gate voltage is higher, it will pass the whole voltage. If it is lower, it will not pass. But still, you have to remember. Okay, this will be Vd minus. Sorry, this will be Vd minus Vth, right? And things you have to remember. But it's better if you do the analysis, you'll understand a lot about MOSFETs. Okay, yeah. Let's solve the next question. This is the next question. Consider the circuit shown with an ideal long channel NMOS. The transistor is appropriately biased in saturation region. VGG and VDD are there. The small signal AC input voltage. So VDD such as it acts as a linear amplifier. Vi is the small signal input voltage. VA and VB represent the small signal voltages at the nodes A and B respectively. The ratio of V over VB. Okay, pretty interesting question. Simply we have to do the small signal analysis. So what will be VA? So if I draw the circuit, your VDD will be shorted, correct? And your the MOSFET will take some current, right? What will be that current? So this is again shorted. So the current will be, okay, this is interesting. This potential is VB, right? And this potential is VI. So current will be GM VI minus GM Vi minus Vb. That is the current that the MOSFET will drive. Okay, yeah, that is the current that the MOSFET will drive. And this again, this point potential is Vb, this point potential is Va, small signal Vb and Va, and this is 2 kilo ohms. And we know what is this current. This current is nothing but Vb by 2. So that would be equals to Gm Vi minus Vb. Okay, Gm is in milliampere, so millisiemens. So automatically units will be properly taken care of. Okay, and this is again 4 kilo ohms of current. We don't even need to calculate all this. This is there just for show. So what is happening? This current, right? This MOSFET current ID will be same as this current, right? Because it is in series, everything is in series, right? So what is your VA? VA is equals to minus 4 into ID, if you see, right? Because ID is in opposite direction, correct? And your VB is equals to 2 into ID. So your VA over VB equals to minus 2. Okay, V over VB is minus 2. So you don't even need to solve anything, everything will be cancelled. So that will be your answer. Minus 2 would be your answer of this question. Let's solve this question. Okay, there are how many? I think there are almost, okay, 20. Lot of questions. MOSFET has lot of questions. Yeah, let's solve these questions. Yeah, consider an ideal long channel N MOSFET enhancement mode with gate length this. So L gate length is this and width is this. So L is 10 micrometer and channel width is 100 micrometer. So W by L is 10, right? The product of the electron mobility mu1 and oxide capacitance per unit area Cox is mu1 Cox, that is equals to 1 milliampere per volt square. Okay, the threshold voltage of the transistor is 1 volt. Okay, so Vth is 1 volt. For a gate to source voltage VGS, that is 2 minus sine to t volt. Drain to source voltage VDS is equals to 1 volt. So this is always constant. It is connected to source. So VDS is constant, that is 1 volt. Right. The maximum value of drain to source current would be what? Okay, this is interesting. So VDS is constant. So if you see, if you observe one thing, your VGS can be, the minimum value of VGS is 1 volt when sine 2t would be minus 1. Sorry, when sine 2t would be plus 1. Right. When sine 2t would be minus 1, your maximum value of VGS would be 3. Okay, and we certainly know that the current of the MOSFET depends on VGS. It certainly depends on VDS as well. It depends on VGS as well, right? So if the VGS is 3, so what will be your VDS? So VDS must be, if it has to be in saturation region, this has to be, VDS has to be greater than, so VDS, if the MOSFET has to be in saturation region, because we know we get the maximum current when it is at saturation region. We'll have to consider many things here. Okay, so for it to be, let's assume that what is the condition for it to be in saturation region, right? So for it to be in saturation region, VDS must be greater than VGS minus VT. So VDS is 1 volt, that is fixed. VGS is this 2 minus sine 2t. So 2 minus sine 2t minus 1. VT is 1, right? Yeah. So basically this will go there 2 2. So basically your sine 2t greater than 0. So whenever your sine 2t is greater than 0, then the MOSFET is in saturation. Whenever the sine function is greater than 0, MOSFET is in saturation. Otherwise it is in linear region. Okay, so let me write the expression of current for both the cases. Okay, so what is the expression of current when it is in linear region? It is mu n Cox. So let me write this as Kn. Okay, that is just some constant, does not matter, into VGS minus VT. VGS is 2 minus sine 2t into VDS. VDS is 1, right? It is in linear, minus VDS whole square by 2. VDS is not small, so I cannot ignore the term VDS whole square by 2. That is the current. Now when will this current be maximum? Right, when this negative sign will be minimum. So when this will be minus 1, right? And so in this case, right, this is the case condition when my sine 2t is less than 0, right? When sine 2t is negative, then only my circuit will operate in linear region. So if it is negative, I can consider the lowest voltage minus 1. So if I consider minus 1, your current would be Kn into 3 minus half, that is 2.5. So it is 5 Kn by 2. Okay, now when sine 2t is greater than 0, then the current equation of MOSFET is equals to Kn by 2. So Kn, I have assumed it to be Kn is equals to mu n Cox into W by L. Okay, so this would be equals to this VGS minus VT whole square. So VGS, okay, hold on, this is only VGS, right? I forgot to write minus VT as well. Sorry. Here there will be minus VT as well. Yeah, minus VT. So this actually will be 1, that is 2. 2 minus half, that is 1 by 2. So this will be 1 by 2 actually. Hold on, sorry. Minus of this 2. 2 minus, sorry, this will be 3 by 2. Yeah, 3 by 2. 3 by 2 can. And here this will be VGS minus VT. So sine 2t minus 1 whole square. Right. Now when this term will be maximum? When sine 2t is again smaller, because this is negative. So what is the smallest number that I can choose? Sine 2t equal to 0. So I will choose this equal to 0. So this will be Kn. This will be 0. So this will be 2 minus 1, that is 1. So Kn by 2. So actually I get the highest current when it is in linear, not in saturation. Right. So what is my Kn? Kn is mu n Cox, that is 1 milliampere per volt square into 10. So it is 10, right? W by L, that is 10 milliampere. So whatever is the unit, but essentially the unit is milli. Okay, remember this the unit is milli, right? Now if I multiply Kn with this, so my ID, the maximum value of ID would be 3 by 2 into 10 milliampere, okay? Because this was in milli, here this was in milliampere, that's why everything will be milli. Rest of the things are in SI units, so I don't need to worry about them. So this would be equals to 15 milliamperes. 15 milliamperes. So your maximum current would be 15 milliamperes. So you cannot go beyond that, right? If you see in saturation, you're getting a maximum current of 5 milliamperes. So few people would tick mark this. So that is where you might go wrong. Okay, let's solve this question. In the circuit shown, V1 and V2 are bias voltages. Based on the input and output impedances, the circuit behaves as what? Okay, so based on the output impedances, circuit behaves as what? V1 and V2 are bias voltages. So if they are bias voltages, they will be simply like shorted for small signal analysis, or they will remain constant for small signal analysis, right? So is it a voltage control current source, current control voltage source, what kind of thing it is? So if I compute the input impedance, right? So one thing, if I remember that this you have to remember, right? So if I have a MOSFET and I'm observing the impedance from the source, do remember what used to happen? Whatever is the impedance here, right, Rx, this is essentially a drain connected MOSFET. This impedance is simply 1 by Gm. For the students who don't understand this, ignore this, derive it properly. Okay, ignore this part, derive it properly. I will not explain the longer process because for that course is there, not course, you can go in YouTube and watch that. Okay, so yeah, this will be 1 by Gm and this will be boosted. So this will not be boosted, this will be divided. So the impedance that I see at the source will always reduce. Impedance will be very smaller because this will be reduced by the factor of Gm RO, whatever is the impedance here, right? Gm RO. So impedance seen from the input side is very low. So Ri is low. And similarly, if I see the impedance from the output, right, this resistance will be boosted. The impedance will be magnified. So the impedance that I see from the output terminal is high. Okay. So let's discuss about this topologies a bit, right? So if your output impedance is high, so let's say this is my amplifier, right? And this amplifier has a output impedance RO. Okay, and you are connecting a load, right? You're connecting a load. Now if your output impedance is high, then approximately you can consider this to be open. So whatever current I am sending here, all of the current will be flowing through the load. So that is a very good property of a current source, right? If your output amplifier of this amplifier, if your output impedance of this amplifier is very high, whatever current I send here, right, all of it will reach to the load. Is it true for the voltage as well? Voltage, it does not matter. If I apply a voltage here, right, it won't matter. Okay, because this voltage will be same only. So output impedance high does not help in that. Okay, I'm just telling you how to remember these things. Okay, so if the output impedance is high, certainly it will act as a current source. To the load, it will get a constant current. So basically, connecting the load does not have any loading effect. If this load impedance is high, it does not matter, right? So because R0 is tending to infinity, so whatever current I send here, right, all of it will go here. It will not choose this R0 path. So this current is always coming, whatever current I'm sending from the amplifier, it is reaching here. So it is acting as a current source. So whenever your RO is high, always remember it will act as a current source. If your RO is low, then it will act as a voltage source. Okay, how? So if your RO is low, right, then you will not assume this to be in parallel, you will assume this to be in series. Okay, and here you will have a loading effect. Here you will have a load. Now if your RO is low, right, if your RO is low, then let's say if I apply a voltage here, VO, then all of the drop will be occurring across the load. Because RO is almost low, that is 0, all of the drop will be occurring here, right? So if your RO is low, then it will act as a voltage source. If you think, sir, you applied, like you have drawn the circuit RO in series with RL, that now you're drawing RO in parallel. So it depends, right? If you think that RO is very low and if you draw in parallel, nothing will happen. So all of the current will come to the through the output resistance path, and the voltage also will become 0, right? Because if your RO is low, the voltage also will be 0, so nothing happens. So when your RO is low, don't connect it in parallel, connect in series, and then think what can happen. So it will be always behave as a voltage source. Okay, it will always behave as a voltage source. So with the output impedance, you decide what kind of source you are acting with, right? Because ultimately you connect a load to get a signal, either the voltage signal or the current signal. So here I am getting a constant current signal, and in this case I will get a constant voltage signal. Okay, so that is how you define the RO. What about your RI? What will happen to your RI? So RI is the input impedance, right? So RI is here. Okay, now let's think from the input perspective, right? So a source is controlling it, and RI you're telling is very high. So if your RI is very high, and if I assume that it's a voltage control source, that means your input source is a voltage source Vs, and Vs will have a source resistance which is generally very small. So, and if your input resistance is very large, sorry, is very in this case is very low, what will happen? The voltage signal will not properly come here, right? Because if it was large, then all of the voltage drop would have been coming across the input resistance, and I would have been able to amplify that. That means this is wrong, right? This circuit is wrong. So assume your input to be a current source. If I assume my input to be a current source, let's say Is, and if your input resistance is very small, right? Your current source also will have a source resistance that will be very large for a current source, and it will have a input resistance from the MOSFET amplifier that will be later used to amplify the signal. So if your Ri is small, then whatever current signal I send here, all of it will go to the input resistance. So what is happening? I'm getting all of the input signal to amplify, right? So whenever your Ri is low, it will behave as a current source. Whenever your Ri is high, it will behave as a voltage source. Like you can do the same analysis. In this case, our Ri is low and our RO is high. So it will behave as a, sorry, not current source, sorry, it will be current control, and this will be voltage control. So in this case, our Ri is low and RO is high. So it is a current control current source, that is D. Okay, that is E. That's all. A cascade of common source amplifier in unity feedback, for which configuration oscillates. Okay, so a cascade of common source amplifier in unity feedback. Okay, so this is a common source amplifier, and they are cascaded together, right? So the output stage is directly connected here to the input of the next stage. Okay, with a feedback, with a unity feedback. So basically the output is directly connected with the, wherever there is the, so whenever I have a feedback, right, what happens? So there I have a forward path gain, then the output VO is connected to the input in the mixing stage, right? This is VI, this is VO. So where will it be connected? Somewhere, I think somewhere in this stage. So this is the output, right, that we take in a common source amplifier. So this stage will be somewhere, this is VDD, VDD. Somewhere here there will be some mixing circuit that will be used to mix the feedback and the input, obviously. Okay, I'm just drawing this roughly. So for this, for the system to oscillate, we know that your overall loop gain, right, mod of A beta must be greater than or equals to 1, okay, or greater than 1 to be specific, for it to be, for we to have sustained oscillations. And your overall phase loop, right, phase loop, this loop must be 0 degree or 360. Okay, so in this case, the closed loop gain is less than 1. So we are giving unity feedback and the closed loop gain is less than 1. Okay, actually this technically, so I think they gave empty this question. So I think they mentioned, they tried to tell that loop gain, they were talking about the loop gain. So if the loop gain is less than 1, there will not be any sustained oscillation. The loop gain is greater than 1 and the phase shift is less than 180. Okay, so phase shift is less than 180. So already this two MOSFETs provide a phase shift of so this provides a 180 phase shift, this already provides a phase shift of 180. So I don't need another phase shift, right? That is wrong. No, actually the phase shift should be 0 degree, because already they are providing 360. So all these options are wrong actually. So these are the two conditions that you must use. First of all, they should not use this closed loop gain term, they should use only the loop gain term. Okay, and the phase shift is this, right? So yeah, I think this question was empty, so we can ignore this question for now. Let's solve this question. So in this circuit, you will have to solve the value of VL. Okay, so nothing is mentioned, you will assume everything to be in saturation. So this current is 0, this current is 0, this current is also 0, right? Hence this current will be 1 milliampere, and this is acting as a current mirror. So the current will be scaled with respect to its W by L ratio. So this will be 10 milliampere, right? So this current is 10 milliampere. Now this current is 10 milliampere, right? And this current is 0, this current is 0. So this current is also 10 milliampere. Cool. So again, there is some scaling happening over here, right? So again, they are in current mirror. So this current will be 5 milliampere. 5 milliampere. Okay, I'm not writing milli, but you get the point. So this current is 5 milliampere. Okay, what about this current? Again, these two are in current mirror, right? So if this is 10, this will be scaled to 7 milliampere. I'm just solving this in a fast manner. This is 1, all these three are in current mirror, so this will be 7. Now this current is 7, this current is 5, this current would be 2 milliampere, right? So VL would be equals to 2 milliampere into 1 kilo ohm, that would be equals to 2 volts. Okay, so your VL would be equals to 2 volts. That's it. This is your answer. VL is equals to 2 volts. Okay, so that is it basically. And yeah, let's solve this question. So here they want you to find out the circuit below. Long channel LMOS is given, the small signal transconductance is GM. Channel modulation you can ignore, the small signal input impedance. Okay, they are asking you the small signal input impedance, right? So if you assume this to be some potential Vx and this to be some current Ix, right? So your ratio of Vx by Ix would give you the small signal input impedance. Now what is happening? This is Vx, right? This is Vx and this is some voltage V. Okay, here there is no current, 0 ampere current. From here there will be some current. What is this current? This current will be Gm into Vx minus V, correct? This potential is V, this potential is Vx into Vx minus V. And what about this current? So this current would be, that is flowing here, that would be 1 by j omega C1 into Vx minus V. Okay, Vx minus V. So yeah, now I can apply a bit of KCL, right? I can apply a bit of KCL. So this is my Ix. Okay, if I apply KCL at this node, your this value, right, Ix current, this will be equals to this current. Okay, there are two incoming currents, right? Ix and this current, right? That is equals to plus Gm into Vx minus V. Okay, this is equals to V by Okay, sorry. This will be multiplied, right? Not divided. Sorry, this will be multiplied, right? Because this is 1 by 1 by j omega c. So this also will be multiplied j omega CL into V, basically that is the voltage, right? So from this equation I will be able to calculate what is my V, right? Or I will be able to calculate what is my V minus V, Vx minus V, right? Because Vx minus V is related with Ix, so I will be able to comment on that. Okay, but that will not help because V minus Vx will be in terms of V, that is what I don't want. I want Vx by Ix, right? So ultimately let us solve for V. Okay, so if I solve for V, so this will be j omega c1 plus gm, yes, j omega c1 plus g1 gm, uh, and okay, this is there, right, into Vx is equals to, that will go that side, this will be j omega cl plus cx plus gm into V. Okay, so yeah, now yeah, if I solve for this, this will be, yeah, if I solve for V, right, V would be equals to this whole thing divided by this thing, right? This thing divided by this thing into Vx. Okay, now we can solve it. Okay, becomes a big expression, but yeah, we can certainly uh, solve it. So if I solve it, right, if I solve it, what will I get? Okay, we get a very big expression. So Ix is equals to this, right? So let me replace here V with whatever value I have just computed. So if I replace V with whatever value I have just computed, this is my Ix, that is equals to 1 by j omega c1 Vx minus V. So yeah, if I take V minus Vx minus V, so I can take Vx common, and this would be uh, okay, Vx minus V, right? So this whole thing will be there, minus will be there, so what will happen is gm by j omega cl plus cx. So your Vx over Ix would be equals to, so this j omega jj will be cancelled, omega, okay, hold on, jj will not be cancelled, I'm sorry, jj will not be cancelled, j and j will be multiplied, so this will become minus 1. So this will go on that side, so minus omega square into, what is this, this is c1, right? Yeah, c1. Okay, c1 is there. Okay, what is cx? I don't know what is cx. What is cx, by the way? G omega, okay, sorry, this is supposed to be c1, right? Sorry, cl, okay, sorry, this is cl plus c1. What is cx? Cl plus c1, okay, cl plus c1. So omega square into c1 into cl plus c1 divided by gm. Okay, so yeah, are we seeing something like this? Yeah, GM. Okay, I'm doing something. Oh, okay, omega square should be at the bottom, not at the top. So I'm doing some sort of silly error. Let me just quickly check. Oh, sorry. Here also I've written it wrong, right? This will be sorry. This will be j omega into c1, right? Yeah, I'm just writing this wrong. So j omega into c1. Right, so j omega will be cancelled actually. Sorry about that. So that will be cl plus c1 divided by gm. Okay. Am I correct? So this comes out to be okay. So I'm doing some mess up. Okay, some mess up I'm doing. Let me just quickly calculate. This is vx minus v into j omega c1. Correct. J omega c1 into vx minus v, that is the incoming current, plus another incoming current gm into vx minus v, that is equals to j omega cl into v. So this, if I add these two up, this will be j omega plus c1 plus c1 plus cl plus gm plus j omega c1 plus gm v equals to, so yeah, v is equals to this, right? J omega c1 plus j omega this. Now what happens? Okay. What am I doing, man? There is a plus gm as well. Really, I'm not doing something weird. Okay, j omega c, and if you subtract this, so actually in the top I will have j omega cl, I will have, right, plus j omega cl will still be there actually. I'm just solving in a hurry, that's why I'm making a mess of it, I'm sorry. So yeah, this will be now if I put it on that side, uh, okay, what will happen? uh, this will be 1 by j omega c1 into j omega cl plus c1 plus gm divided by gm plus j omega cl. Okay, so yeah, this would be equals to this would be equals to what? This would be equals to what? Yeah, I was just getting stuck, but this gm will be, that's why you should not do in a hurry. This gm will be cancelled, so you just put the value of v here, right? Put the value of v, your gm also will be cancelled, right? I was missing this point. Only what will remain actually? Only j omega cl will remain. I'm sorry about that. J omega cl will remain at the numerator. So if this is only there at the numerator, right, this will be j omega cl. Okay, yeah, now I think we should be able to crack it. So yeah, if I break this down, this will be j omega will be cancelled, this will be 1. So this will be 1 by j omega c1. Okay, and next this will be j omega cl will be cancelled, this will be 1 by j omega cl, and this will be minus gm by omega square c1 cl. Okay, c1 cl. So you just solve this, you will get back to this equation. I was just messing up few things. So yeah, I think your answer would be option A, right? 1 by j omega c1. Yeah, this will be minus, not plus. Yeah, A will be your answer. Okay, bit lengthy, just calculative. Okay, so you will have to be good in calculations. So this is the next question where we have been given, we have to calculate the for the closed loop amplifier circuit, the magnitude of the open loop low frequency small signal gain is 40. Okay, all the transistors are biased in uh, Closed loop amplifier shown in the magnitude of the open loop low frequency gain is 40. All transistors are biased in saturation. ISS is ideal. Neglect channel and modulation. The closed loop low frequency gain would be, okay. So they are asking what is the closed loop gain if the open loop gain is what? Open loop gain is 40. Okay. So what is the feedback factor here? How do you compute the feedback factor? So if you see that this output is directly connected to the input, right? So if you remember the block diagram of amplifier, there I have a gain A, and then this output V out is directly connected to the input, right? This is my input which is directly connected here. If you see this output is so this was, so if this loop was not there, so these are my inputs, right? And this was my outputs. Only this, if this loop was not there, okay. Now we are directly connecting into the input. If you see the output is directly connecting to the input, correct? So here your feedback factor beta is 1, and it is a negative feedback system. If it's a negative feedback system, the gain would be A upon 1 plus A beta, that is equals to 40 upon 41, okay, which will approximately be 0.976. Okay, so this shall be your answer for the question. So yeah, I think a bigger explanation is there on our playlist, so you can go and watch there, because I will have to solve more questions. So I'm not totally going into this question. There are a lot of things into this question. I'm not going into that. I'm just showing you the easy solution. If you want to have a comprehensive solution, you can watch the analog electronics playlist. There I think this question was solved comprehensively. Okay, let's solve this question. In the circuit shown below, the transistors M1, M2 are biased in saturation region. Their small signal transconductance GM1 and GM2 respectively. Neglect body effect, channel length modulation, and intrinsic device capacitances. What is the V over Vin, right? Assuming C1 acts as short circuit during AC analysis. Okay, V over Vin, that is what they are asking me. Okay, V over Vin, right? So V over Vin, how do I calculate? So so in small signal analysis, this will be open circuit, right? This will be short circuit. Okay, and what is the input source that I am observing? So if I see what is the input impedance seen from here, so this is infinity, right? Gate does not drive any current, that is infinity. So this is RB, okay, and what is the impedance seen from here? It is simply 1 by G, correct? This impedance is simply 1 by GM. Impedance of this MOSFET is 1 by GM. Again, if you're not understanding what am I talking about, you will have to revise MOSFET more. Okay, so this impedance, because it is a diode connected impedance, I can replace this with 1 by GM in saturation region. So this whole impedance is RB plus 1 by GM. So technically what is happening, I have a RS impedance over here, and I have a 1 by GM plus RB impedance, and I have here my Vs. Okay, so this is my Vs and this is RB plus 1 by GM, right? So this is the node voltage. Let's assume this node voltage to be Vx. So your voltage Vx will be simply voltage division, that is Vs into 1 by Gm plus Rb upon Rs plus 1 by Gm plus Rb. Okay, so yeah, now we know this. Now what will be this current? Basically this will be Gm2. Okay, this is not 1 by Gm, this is 1 by Gm1 actually, because that is the MOSFET M1, right? So this will be GM1, this will be GM1, and this will be GM2 into whatever is the voltage Vx, that is the current through it, right? And this current is in series with this. So your V out, again, it is just like a common drain amplifier. I'm solving it very fast. If you're not understanding anything, maybe you need to revise a bit. Okay, so this will be your VO would be minus GM2 into RD into Vx, right? This node potential Vx. So that is Vx. So your VO over Vx. So I don't need Vx actually, right? I need V over Vs. So I'll replace Vx with this particular expression. So this is your Vx, and I can replace my, I can take my Vs on the other side. So this will be equals to minus GM2 into whatever was the coefficient in the previous case. So GM2 into 1 by GM1 plus RB divided by RS plus 1 by GM1 plus RB. So minus of, okay, they're asking me mod. If they're asking me mod, so it won't matter basically. So negative will become positive. Ultimately, I will just have to take the terms, right? So GM2 RD is also there. Don't forget RD. Sorry, RD is also there, right? GM2 into RD into 1 by GM1, GM2 into RD into 1 by GM1 plus RB divided by RB plus 1 by GM1 plus RS, right? This is actually, here there are three terms. No, there is just the inverse. No, option B is absolutely correct, right? Option B is certainly correct. Okay, GM2 into RD into 1 by GM1 plus RB, right? Okay, so option B is correct. Okay, so yeah, option B is correct in this case. If you're not able to understand, again you have to revise, like what is the input resistance for a common diode connected MOSFET, what is the expression for a common source amplifier, right? How to calculate the voltage division, all these things you will have to revise. Otherwise, solving this question with basics will take a huge amount of time. You will not be able to solve that. Let's solve this question. In 2024, a lot of questions came from MOSFETs, right? A lot. An NMOS transistor operating in linear region, IDS is equals to 5 microampere, right? So it is operating in linear region, and your drain to source current is 5 microampere. Okay, and your VDS is equals to 0.1 volt. Okay, keeping VGS constant, VDS is increased by 1.5 volt. Okay, so we're keeping VGS constant and we're increasing VDS to 1.5 volt. Okay, the new operating region would be, okay, so VDS is very small if you see, right? So I can compute few things. If it is in linear region, so it will be Kn mu n Cux into W by L into VGS minus VT whole VGS. So have they given VGS? They have not given VGS. So let me assume VGS as V only minus VT. Let me assume VT as VT only, VGS minus VT into VDS. VDS is 0.1. Okay. Now actual expression will be VDS square by 2, and as VDS is 0.1, VDS square would be 0.01 and by 2 would be 0.05. That will be very small compared to this number. Okay, so we can safely ignore this. So approximately, yeah, this will be the expression, and they have already given what is mu on Cux W by L, right? They have given the value of Kn, that is 50. So I can get my value of V minus Vt into 0.1, that is 50 into 0.1, that is 5. So V minus Vt is 1 in the first case. Okay, V minus Vt is 1, or let's not ignore VDS square by 2. Let's actually keep it. It will not make much of a difference, but let's just keep it. Okay, so I think that will, change our answer. So this will be basically 0.1 whole square by 2, that is 0.05, right? So this will be 50. 50 will be gone there. remember this is already in microampere, this is also in microampere. So micro will be cancelled. This will be 0.1, 0.1 minus point. Okay, that will this actually does make a difference. Okay, so this is 0.1 minus 0.05, that is 0.05 into 10, that is 0.5. Okay, just give me 1 second. VDS square. Okay, sorry, this will be this 0.005. I'm sorry, 0.005. So this is 0.1, then this will be subtracted, sorry, minus VDS square by 2, right? So this will be added. So 0.1 plus 0.05, that is 0.1 into 0.1. So this will be converted. V minus VT is equals to 1.05, right? 1.05 volts. V minus VT will be equals to 1.05 volts. That's it. Now we got our V minus VT. Now, yeah, we got our V minus VT. Now how to solve this? Now how to solve this? The new operating point. Keeping VGS constant, VDS is increased to 1.5 volt. Yeah. So now what they are doing? Essentially, they are keeping VGS constant. So this is constant actually. They are increasing VDS to 1.5 volts. The transconductance at the new operating point. So for that, first of all, we have to discuss. So they are keeping VGS constant, right? So they are keeping this V constant. So your VGS minus VT, that VGS is this, right? So VGS minus VT, that is equals to 1.05, that is constant. Okay. Now they are increasing their VDS to 1.5 volts. So your VDS is greater than VGS minus VT, right? Because VGS is constant and VT is anyways constant. So your MOSFET is now into saturation region and your transconductance is defined in saturation region only, correct? And do remember what is the transconductance? So what is your current? So transconductance is basically the change in the drain current with respect to VGS, right? Input voltage. So that is equals to my GM. So how do I calculate that? So we know that the drain current of the MOSFET is Kn by 2. Okay, Kn is just a constant into VGS minus VT whole square. If I differentiate this, what will I get? If I differentiate this, this will be del ID upon del VGS, that is equals to Kn into VGS minus VT, right? Kn into VGS minus VT. Okay, so yeah, so essentially, right, your GM is equals to Kn into VGS minus VT, that is basically mu n Cux W by L into VGS minus VT. What is VGS minus VT? It is 1.05, that is constant, right? VGS minus VT. So mu n Cux W by L is actually 50 microampere per volt square. So 50 microampere per volt square into VGS minus VT. So VGS minus VT would be equals to 1.05, right? So this would be equals to 50 into 1.05. So 52.5. Okay, 52.5, right? Micro ampere per volt. And what units they have asked? They have asked in microampere per volt only. So 52.5 would be your answer for the question. If you don't if you neglect that point 1, right, that will actually cause effect. So don't neglect it. Don't neglect it. Let's solve the next question. This is the next question, right? That came in gate 2025, and in 2025 as well there were mostly 2 questions from MOSFETs. Let's solve this question. So which of the following is true with respect to DC coupled single stage amplifiers having finite load resistor? Okay, the common gate amplifier has an infinite input impedance. So common gate meaning the gate part is common, gate cannot work as an input, your input is the source and your output is your drain, right? And we know in common gate, if I see this resistance, right, this resistance is very small, so input resistance is actually very small. Okay, it is not infinite, it is almost close to 0. Ideally it will be 0. Okay, so wrong. First option is certainly wrong. Second option, the common source amplifier has an infinite input impedance. Common source amplifier, certainly yes. Common source amplifier, what is input? Gate, and gate does not take any current, so finite voltage upon 0 current is infinity. So certainly common source amplifier will have an infinite input resistance. The input and output voltages of common source amplifier are in phase. Certainly they are not in phase. There is a phase difference between the input voltage and the output voltage of 180 degrees, because do you remember what is the gain? The gain is minus GM/RD, right? So there is a negative sign. The input and output voltages of common drain amplifier are in same phase. Yes. So the gate and source will have same phase. This you know, and this you can derive as well. The expression, the gain expression will not come out to be negative, it will be positive. That means your input voltage and your output voltage are in same phase. So option D is also correct. So B and D are the correct answers for this question. Let's solve the next question. This is the next question. The identical MOSFETs M1 and M2 in the circuit given below are ideal and biased in saturation region. So both of them are in saturation region. They are identical and have conductance GM of 5 millisieverns. V1 is this voltage, V2 is this voltage. The output signal V3 would be what? That is what they're asking me, right? If they are identical, right, so this also will have 1 milliampere of current, this will have 1 milliampere of current, and I see that they are biased with same voltages, only there is a difference of in the small signal AC voltage. So what you can do, you can simply solve using half circuit. Okay, using the concept of symmetricity you can solve it. Okay, so they are asking you, okay, yeah, they are asking you this V3, right? You can directly solve for V3. So if you know by virtual ground concept that what will happen, let's assume like this potential will be 0 actually. Why this potential will be 0? Because in small signal AC this current source will be open circuited, no current will be flowing through here. If I assume this potential to be V, so from here some current is flowing, GM Vi minus V, and from here, so this is Vi by 2, right? This is the half voltage. So if you see this half voltage I am applying here, half voltage I am applying on this side. Okay, and this is negative, right? This voltage is negative. So okay, let's assume that I am doing the small signal analysis, so these voltages are 0, these are large signals. Okay, so this is plus Vi minus Vo, and this voltage, right, will be GM minus Vi minus V, right? Because here V is negative basically, that's why I'm assuming Vi to be 0.01 sine omega t. Okay, and again this is also short circuited. So if this is short circuited, okay, two currents can flow. Okay, so what will be your V basically? It is negative, right? So so what happens is this addition of these two currents must be 0. So if I add these two currents, GM Vi minus V plus GM minus V, minus V equal to 0. So these two will be cancelled. So from here Gm is not 0. So you can certainly say that V will be equals to 0. Okay, that it acts as a virtual short. Okay, so it is nothing but virtual short, right? Okay, cool. Now I can solve for only the half of the circuit. Okay, you can solve only for the half of the circuit because they are asking about V3. You can compute that. So if I solve for half the circuit, this is the concept of half symmetry. You can obviously see this video there on our YouTube channel. I think this is there already, so you can go and watch that in the MOSFET marathon. This video is there already. Okay, and this will be ground, basically virtual short, not exactly ground but virtual short. This is my input, right? So what is the gain of this amplifier? Minus Gm into Rd. Rd is 1 kilo ohm, so it is 1 only, into, yeah, minus Gm into 1 basically, right? So that this is a small signal gain. I just need to compute Gm. Gm is given to me, that is 5 millisiemens. So, and your 1 is 1 kilo ohms, so milli and kilo will be cancelled. This will be minus 5. So the small signal gain is minus 5. So if I am applying a voltage, small signal voltage of 1 volt, here at the output I will get a voltage of minus 5. Okay, small signal does not mean that this amplitude is small. No, small signal basically means compared to the DC signal it will be much smaller. Okay, that is what small signal means. So the small signal V1 will be amplified by a gain of minus 5. So if this is 0.01, so your small signal will be amplified by minus 5 into 0.01, that is minus 0.05. that I can see only in option D. So certainly option D will be correct, certainly it will be correct. But what about 4? So we only discuss about the small signal, right? We did not discuss what is the value of the large signal. So what will happen to this 2.5? Okay, so we know now all this is analysis is done. So I will delete all this. Okay, these two circuits are identical, and initially I told you this current is 2 milliampere. So this current will be 1 milliampere, this current will be 1 milliampere. If this current is 1 milliampere, what is the drop? 1 milliampere into 1 kilovolt, that is 1 volt. So can I compute the voltage here? This is 5 volt, there is a drop of 1 volt, this will be 4 volt. Does it make sense? Yes. If it does not, you will need to go and watch those videos. Okay, revise. So option D will certainly be correct. So with this we are done with MOSFETs. Now we will start with operational amplifiers. Steady state output voltage V out of the circuit will be what? Okay, so here there is a constant voltage connected. So if I assume initially if the capacitor is uncharged, okay, so this V out will be coming here, and there will be negative feedback. Yes, there will be negative feedback, certainly there will be negative feedback. And okay, if there is negative feedback, what will happen? So whatever is this point potentials, this point potential will be same, and this has 0 current, right? So if this has 0 current, this point potential will be 0 volt, so this will be actually 0 volt. Okay, so your V out will be 0 initially. Okay, it is 0. Okay, and slowly it will charge the capacitor. If it charges the capacitor, this potential will increase. But if this potential increases, how this V out also has to increase, because there is a virtual ground, right? I'm just thinking. So actually this point potential is 0 only, right? This one potential is grounded because there is like the input impedance of the op-amp is not there. Now this circuit is a if you see, this circuit is an ideal integrator, right? And they have actually provided us the threshold voltages. So certainly this will saturate, because an ideal integrator, we know it saturates, correct? Now which side it will saturate? We know, if you see, your V out will be minus integration of V input dt over RC. Okay, so there is a negative phase shift, so of course it will saturate to minus infinity. right? So minus VE, whatever is the negative voltage, it is saturated, because after, so the graph will be looking something like this. So initially the as my input, right, is a constant voltage, okay? So what will happen, this because this is constant, this is 0.1, so what will happen, this, right, will be equals to 0.1 by RC T minus, so the slope would be somewhat like this would be the slope, okay? And then it will saturate because it is going towards negative, and it cannot go to minus infinity because there is a lower limit, right? So it will saturate to minus VE. This was one of the problems in an ideal integrator. Let's solve this question. There is a next question, right? This question. So here we see the output impedance of a non-ideal operation amplifier is denoted by Z out. So okay, Z out is the output impedance of a non-ideal amplifier. Okay, the variation of the Z out with increasing frequency is best represented by what? Okay, so we know the how does the output impedance vary with respect to frequency for a non-ideal operational amplifier. So for a non-ideal operational amplifier, what happens? So you see there is a feedback connected here, right? If there is a feedback connected, what will happen to the output impedance? The output impedance of a non-ideal amplifier, right? So you see there is a negative feedback, and if there is a negative feedback, the output impedance RO reduces by a factor of 1 plus A beta. Do you know what is A beta? So this is all part of feedback topology, okay? All part of feedback topology. If I have negative feedback, the output impedance would reduce by a factor of 1 by A plus beta, and the input impedance will increase by a factor of 1 plus A beta, Ri dash into Ra, and this will be Ro dash. So these are few properties, right? Now what is the beta? Beta is the feedback factor. So how much of the output is reaching the input side? In this case, if I see, right, sorry, how much is the output? So this is my feedback voltage, right? And you see all of your output is your feedback. So your, in this case, like generally the beta is defined as Vf is equals to beta into V naught. In this case, beta is 1. So actually your output resistance is Ro divided by 1 plus A. Now if I assume my output resistance of the non-ideal op amp to not vary with frequency, okay, if I just consider the loop gain A, okay, what will happen with the loop gain A? So we know the loop gain A, if I do the first order approximation of op amp, it is like this. So at near low frequencies, the frequency response of a op amp is just like a low pass filter first order. Of course, we know the actual frequency response of op amp is somewhat like this, right? This is the actual frequency response of op amp. It is like a band pass filter, correct? Here also, if you see, with increasing in frequency, the gain reduces, right? This is the gain magnitude of omega, or whatever you say, magnitude of A. So gain reduces, right? So this will reduce with increase in frequency. This will reduce. If this reduces, your RO actually will increase, correct? So with increase in frequency, your RO will increase, okay? And then what is the highest value? Will it keep on increasing? No. So what is the lowest value of A? It is 0, right? In dB it is minus infinity, but in decimal scale it is 0. So this will be RO by 1, that is RO. So the lowest value that my A can reach is 0, and this will become RO. So this will be saturating at a certain point, right? And here this will be some constant value. So this will be RO by some, let's say RO by 5, RO by 6, right? So it will be much less than RO. So this will be coming here, okay? So the graph will look something like this, right? So option C is correct. In this case, option C is the answer, okay? Yeah. The current gain I out over I in the circuit with an ideal current amplifier given is what? Okay. So what is the current gain in this case? They're asking me what is the current gain. So this is an ideal op amp. So no current will flow through here. So all of the current will come from here. Now here there will be two divisions. Some current can come here, some current can come here. Okay, how do I calculate it? So what you can do, as it is an ideal op amp, it will follow the virtual short concept. So whatever is the positive side voltage, same voltage will be applied here, correct? So I can actually calculate this voltage. What is this voltage? This voltage is I in divided by j omega Cf, correct? That is the voltage here, and this is my voltage VO, which will be same. So this is the voltage between this point and ground. So same voltage will be between this CC capacitor and ground. So the voltage across the capacitor, right, is minus I in by j omega Cf. Now they are asking me what is the current gain, I out. So I out is this, right? So this will be equals to I out divided by j omega Cc. So ultimately your I, whatever they have asked I out over I in, that is equals to Cc over Cf minus, don't forget the negative sign. So minus Cc over Cf, that is present in option D. So option D is correct for this question. Okay. So option D is correct. Let's solve this question, right? So consider the op amp based circuit shown in the figure. Ignore the conduction drops of diode D1 and D2. Okay, conduction, there is no, they are ideal. All the components are ideal. The breakdown voltage of Zener diode is 5 volt. Which of the following statements is true? The maximum and minimum voltage of VO is plus 15 and minus 15. Okay. The maximum and minimum value of VO. Okay. So let's assume that there is a breakdown of the Zener diode, right? If there is a breakdown of the Zener diode, then this will be replaced with 5 volts like this. For this to break down, of course this point potential must be very high, right? There is some drop. And if I see, okay, interesting. If there is a breakdown here, even if there is a breakdown, right, what does breakdown basically means? Breakdown basically means that current will flow in the reverse direction, correct? If current flows in the reverse direction, then there is some feedback. Yes, there is some feedback. If there is some feedback, then this will work. I'm just trying to think. So if there is some feedback, right, that means current should flow from this to this, correct? Why current? So if there is a breakdown, that breakdown means current is flowing in the reverse direction for this Zener diode, then only there will be breakdown. Otherwise, if it flows in the forward direction, this will just work as a normal regular diode, right? So if there is a breakdown, current is flowing in the reverse direction for this Zener diode, and current is flowing like this. Okay, so this will be hold on a second, plus minus, sorry, I wrote the terminals wrong. This will be plus minus, right? So this will be plus minus like this. Okay, let me copy the circuit. Hold on a second, let me take the screenshot. So yeah, if there is a breakdown, so what happens when there is a breakdown? So this is my Zener diode, right? What happens when there is a breakdown? So the current will flow in the reverse direction and the potential will be constant, right? So that is what is happening. So this I can replace, if I assume this to be in breakdown, current will flow in the reverse direction and potential will be this, correct? Cool. And this diode also will be turned on, right? Because current has to flow in the reverse direction, the diode also will be turned on. And okay, so what is this potential? So this is my VO, right? VO is at a potential of, so if there is a connection between the input and output, so if this is plus minus 5, right, so certainly this will turn off the diode D1, because diode D1 will be reverse biased, because the N junction potential will be higher than the P junction potential, right? That's why this will be automatically reverse biased. This will be open circuit. Certainly this will be open circuit. Okay, even if you consider it open circuit, you see that this point potential is 5, this point is 0. So of course you see that, yeah, it will be open circuit because the N side potential is higher than the P side. Now, so there is a connection between the input and output, then we can certainly say that virtual ground concept will be valid. If it is valid, this will be 0. If it is 0, right, and I have told you that, okay, let's check for the case. So let's check for the highest value of Vin, right? If Vin is 10 volts, this will be 10. So what will be the current? Current will be 10 upon 1 kilo ohm, that is 10 milliamperes. So this is just a virtual ground, right? It's not like a real ground. So no current will flow through here. So all of this 10 milliampere must flow through this side. And we have already established that current will flow in this direction, not in this direction. So our assumption was wrong. But what if your input is minus 10? If it is minus 10, then actually, then this is fine. Then this will be 0 volt here, of course. Then the current direction will be this. Then it is fine. Then current can flow in this direction. No problems. Okay, no problems. Current can flow in this direction. Now, so what will be VO? VO will be plus 5 in this case. VO will be plus 5 in this case. Okay, so yeah, so the minimum voltage of VO is plus 5. There is no doubt about it, no problem about it. Okay, it is not, so this plus 5 is not saturating, so we don't have to worry about it. It is under our saturation limits, we don't have to worry about it, right? So my VO will be equals to 5 volt when my Vi is equals to minus 10. Okay, now what about when Vi is very high? When Vi is very high, if you apply the open circuit test, this DZ will be on. This will work just as a regular diode in forward bias, but D2 will be off. But this point potential will be very high compared to D1. So D1 will be turned on. If I assume D1 to be turned on, so let's assume that, right? If I assume D1 to be turned on in the second case, right, when my Vi is very high, so all this will be turned off. Right, so this will be on. So this point potential will be plus 10, right? So again the current that would flow is 10 milliamperes in this direction. So again virtual short, that's why 10 milliamperes. Again no current will flow through here. All the current will flow through the diode from P to N, no problems. If it flows from P to N, what is this voltage? It is 10 milliampere into 1 kilo ohm, that is 10 volts. So the voltage drop across the resistor is 10 volts, and this is virtual short. So I am getting VO as minus 10, which is again within my limits. So the lower value of voltage would be minus 10. So that's your solution. So your answer is option D. That is how you solve this question. Okay, you check for the highest and lowest value of the input, and you check what are those values. Whatever we calculated, if one of the values, let's say this value, let's say this resistor was 1. Or let's say this resistor was 2 kilo ohms. If this resistor was 2 kilo ohms, then your answer would not have been 20 volts, minus 20. Your answer would have been minus 15, because after that the op-amp will saturate. Got my point? Cool. Okay. So yeah, so answer for this question would be option D. Right. Let's now solve the this as the next question. The difference amplifier is shown. Assume the op-amp to be ideal. The CMRR of the difference amplifier would be common mode rejection ratio in dBs. Do you remember what does common mode rejection ratio mean in dBs? So it's very easy, right? Very easy to remember. So you know, for an ideal op-amp, the common mode rejection ratio is infinity, and you know that it will be either AD upon AC, differential gain upon the common mode gain, or it will be the common mode gain upon the differential gain. you know CMRR must be infinity. So, and for ideal op amp, differential gain is good and common mode gain should be 0, right? So certainly this will be the formula. That's how you remember it. So your CMRR is equals to 20 log, because they have asked in dBs, it will 20 log magnitude of AD upon AC. Okay. So yeah, this is my CMRR. Okay, let me compute this. So what is the differential gain? How do I compute the differential gain? So differential gain will be, in this case it will be, so in case of differential gain, you apply your input, one of the input to be plus uh, Vi by 2, the other input to be minus Vi by 2, right? And your differential gain AD is actually equals to VO in this case upon Vi1 minus Vi2, that is simply Vi. Okay, that is how you compute the differential gain. Okay, so yeah, it is but tedious, but we will do our best. So if I'm giving Vi and Vi2, right? So here we can see that this will work as a voltage divider. Okay, so if this works as a voltage divider, I'm calculating AD right now. I'm not calculating AC. I'm calculating AD. So this voltage would be this will be simple Vi by 2 into 101.5 divided by 110. So 111, yes, 111, yes, 111. Okay, that is the voltage here. And again we can apply a simple KVL here, Vx, right? That will yield me the VO in terms of Vi1. So if I apply KVL, so this will be Vx minus Vi divided by 2 plus Vx minus VO. Okay, I have to divide by the resistance as well, 101. Okay, so this is equals to 0. Okay, and your Vx is simply this value, okay, which is very weird value. Okay. So let me calculate this. Vx divided by 10.5 plus 101 inverse. This is 0.10514 Vx, and this is equals to 21 inverse plus 1. Okay, 21 inverse and this, right? So let me write this as it is. But what do I want? I want to write my Vx in terms of the other two, correct? That is interesting. So yeah, this would be 0.047, or let me do one thing. So 0.10514 inverse divided by 21. So this would be equals to, Vx would be equals to Vi, and it would be, okay, I missed a point. So this was 117 plus 101 inverse. This into 101 inverse. So this is 0.09 for VO. Okay, that is what my VO is equals to. Now we got our Vx. If I know my Vx, then Vx is equals to this, right? Vx is equals to this. So I can certainly say, okay, hold on a second, this Vi was negative, right? So if it was negative, this will be minus plus, okay, not plus minus, because Vi is minus Vi by 2, minus Vi by 2. The phase shift is just the opposite. So this should be negative, okay. So minus Vi by 2 into 100 1.5 divided by 111 is equals to this, right? 0 0.43, 0 0.453 Vi plus 94 Vo. 0.094 Vo. So yeah, now if I solve this, this would be 101.5 divided by, okay, just 111 divided by 2. This is negative, that will go there, plus 0.453. This this is there, inverse into 0.90, okay, 0.94 inverse. So your VO over Vi is minus 9.683, okay, that is your VO over Vi. This is your differential gain, right? Now what is your common mode gain? So this actually is your differential gain, right? That is what is defined over here. What is your common mode gain? Now your common mode gain would be the gain when from both the inputs I am providing Vi by 2 plus Vi by 2 and plus Vi by 2, okay. So your common mode gain basically is AC, that is VO upon, so this essentially is Vi1 minus Vi2, that is the proper definition of your differential gain. Basically for differential input, what is the output, correct? And your common mode gain would be Vi1 plus Vi2. So overall this should be Vi by 2, then only bottom line, both of them will be same, that's then only this whole addition will be Vi, correct? Got it? Yeah. So yes, now let us solve. So if I provide in the both the inputs Vi by 2, Vi by 2, what will happen? So this side will be same, right? Just instead of minus Vi by 2, I am providing plus Vi by 2 in the non-inverting terminal. So this will be again, the value will be same, but obviously the polarity will be different because now I am providing plus Vi by 2. Got my point? So here this will be Vi by 2 into 101.5 divided by 111, right? Then this would be what? This would be here if I solve this, right, this value now would be again Vx. So Vx minus Vi by 2 divided by, okay, this value will be same only, right, because previously this was Vi by 2 only, so we can reuse this equation. So my Vx will be actually this, we can reuse this because for the inverting terminal it was always plus Vi by 2 only, correct? It was always plus Vi by 2. Okay, one thing I have made a bit of mistake here actually. just a small error. So actually we give the positive input here, okay, that basically plus Vi by 2 actually should be applied here only. So this polarity would be plus minus only. I should give a negative polarity here, okay, but it does not matter, your answer will be same, so don't worry. Ultimately we are concerned about actually, so essentially what is happening, you are doing Vi2 minus Vi1, that's all, that's why it is coming negative. But don't worry, don't take the stress, okay, don't take the stress, it does not matter ultimately, uh, because ultimately we will write the magnitude or absolute value of AD, that is 9.683. So sign would not make any difference, so don't worry about it, right? So I can reuse this equation, as I was saying, we can reuse this equation. If I reuse this equation, from here I can replace my Vx in this equation, right? So Vi by 2 into this will be equals to this. So ultimately again something similar we will get, but with opposite sign. So this will be okay, Vi almost will be equal to, almost it will be 0 but not exactly, or will it be, no, right? Okay. Yeah, here just one small change. Actually the common mode gain we don't actually provide Vi by 2, I'm sorry, we provide, so your common mode gain, right, AC is equals to VO divided by Vi1 plus Vi2 divided by 2, right? That is what we do in case of common mode gain. So yeah, so instead of only providing Vi by 2 here, actually we will provide proper Vi. So if it is proper Vi, then things will change a bit. This will not be by 2 anymore, there will be proper Vi. So this will not be by 2 actually. That is the difference in common mode gain and differential gain. So yeah, just one small change. So in both the terminals I will provide Vi. So if I provide Vi, this will not be Vi by 2, this will be multiplied by 2. Okay, just be careful. This will be multiplied by 2. If it is multiplied by 2, this would be equals to, just the change, what change I have done, this is not Vi by 2, this is Vi, right? Both of them is Vi because your common mode gain is defined like this. So this would be yeah, 0.453 into 2, so 0.96. So this will be 906. Okay, so 15 divided by 111, this so this value is equals to obviously this Vx, so that is minus 0.906, and this would be upon 0.094. So your AC that is your VO over VI common mode is equals to 0.089. Okay, that is the only difference here. So because it will be not Vi by 2, it will be Vi. So you can solve the equations, you will get this value. So your common mode rejection ratio CMRR would be 20 log of magnitude of AD upon AC. So AD is 9.683 log of this divided by AC log of that into 20 should give me 40.68 dB, and that is your answer for the question. 40.68 is your answer for the question. So this is the last question from gate W. So here, assuming op amps are ideal, the circuit represents a summing amplifier. Is it a summing amplifier? It does not look like it, right? If negative feedback is valid, let's check whether negative feedback is valid or not. So here we have feedback, so I'm going through the positive terminals and then I'm coming back. So this is 0 degree phase shift, and here I'm getting 180 degree phase shift, right? So if op amps are not saturated, I can see there is a proper 180 degree of a phase shift over a complete loop, then certainly this will be in negative feedback. I can see this individual op amp is in negative feedback, right? This has a phase shift of 180 degrees in its own loop. So this has a phase shift of 180, this has a phase shift of 180. Okay, yeah, that is the case over here. Now if I solve for this, so suddenly things are in negative feedback. So if it is V in, this point terminal also will be V in due to the virtual ground concept, virtual short concept. This is V in, right? If this is V in, this is also V in. If this is V in, this is also V in. So essentially your V in is equals to V out. So essentially it is just like a buffer, right? Because you're not directly applying, so loading effect is totally gone. Because what you can say is, what if I directly connect through a wire? What's the problem in this, right? Then you also your V out will be equals to V in. No, as soon as you will connect a load here, your V out will not be exactly equals to V in. It will be something less, right? Because here there will be some drop in the source resistance of the input supply, due to which your V out will not be exactly equals to V in. Here it does not matter. Your V out will always be equals to V in. Whatever load you connect, it won't matter. So it essentially works as a buffer. Okay. So with that, we are done with the okay. One more is there. Sorry, one more question is there. So let's solve this question. The pumps in the following circuit are idle. The voltage gain of the circuit is dash. The op amps in the following circuit are idle. The voltage gain in this of the circuit is dash, right? Okay, op amps are idle. So if op amps are idle, so this op amp individually certainly is in negative feedback. This op amp individually certainly is in negative feedback. That can be observed by the loop, correct? Now certainly they are asking me what is the voltage gain. What is voltage gain? Voltage gain is V out over V in. Should have properly mentioned it, but that is fine. What is V in? V in, let's assume this point potential is Vi2 and this point potential is Vi1. Okay, so VO over Vi1 minus Vi2, right? So what we can say is, just give me a second. Yeah, so we can solve for individual, right? So if it is Vi2, virtual short concept, this will also be Vi2. So I can apply a KCL over here. Let's assume that this is some node voltage Vx. Okay, so if this is some node voltage Vx and this voltage is what? This voltage is Vi2, right? And we know no current will flow through here. So essentially these two are in series. These two are in series because no current is flowing into the op amp. So this resistor has a potential of Vi2. What will be the potential here? So this has a potential difference of Vi2. Same current is flowing. This also will have a potential difference of Vi2, right? So your Vx actually is equals to 2 Vi2 because this resistor has a potential difference of Vi2. This resistor also has a potential difference of Vi2. So essentially your Vx is equals to Vi2. Okay. Your Vx is equals to Vi2, correct? Now again what do I see? Again no current will flow through here, right? So again these two resistors are in series, okay, but some current will flow. So some current is coming, some current can flow into the output of the op amp and some current will go here. So certainly these two resistors are not in series, but certainly these two resistors are certainly in series. And what is the voltage here? The voltage here is again Vi2. The voltage here at this point is Vi2, sorry, Vi1, because virtual short concept, this is Vi1. Now certainly what is the voltage across this resistor? The voltage across this resistor would be Vi1 minus 2 Vi2. That is the voltage here, right? Let's assume this voltage to be some VI potential, and this VY potential would be voltage at the positive terminal, that is Vi1, sorry, minus 2 Vi2. That is what is happening across this resistor, and certainly these two resistors are in series. So again this also will have the same potential. So V out will be equals to 2 Vy, because this is plus Vy and this also will be plus Vy because same current is flowing. So Vy would be equals to 2 V, so V out would be equals to would be equals to 2 Vy. So it would be equals to yeah, that is equals to 2 Vi1 minus 4 Vi2. But the problem is we have to find out this value. How do I compute this value? So VO is this. How do I come back to this? Okay, that is certainly not the easiest solution. Okay. Okay. The voltage gain of the op-amps, they're ideal. All the op-amps are ideal. Let me just think. Okay, just okay, is there a small mistake here? This, both of them are same current. So if this, okay, just one small mistake, one small error, right? Yeah, this resistor certainly will have a potential of plus minus Vy, but what is the V out potential? V out potential is not 2 Vy, right? V out potential is 2 Vy plus whatever is the potential here, because this potential is not with respect to ground. So I certainly have to write here plus Vx. So just a small mistake. Properly write the potentials, right? Potential here will not be 2 Vy because this point potential is not 0. So it is not 2 Vy. Certainly this point has some potential, that is Vx. So it will be 2 Vy plus Vx. Just a mistake on my behalf. So it will be 2 Vy plus Vx. So what is Vx? Vx is equals to 2 Vi2. So actually this will become 4 Vi1 minus Vi2. So your Vo is actually equals to 4 Vi1 minus 4 Vi2. So if I take 4 common, divided by Vi1 minus Vi2. So certainly your answer would be 4. So 4 would be the answer of this question. Am I correct? Just give me 1 second. So this is Vy, 2 Vy plus Vx. What is Vy? Vy is Vi1 minus 2 Vi2. Okay, Vi1 minus 2 Vi2. So this will be 2 Vi1 minus 4 Vi2, and then I'm adding plus 2. Okay, sorry, not 4. That's what happens when you're in a hurry. It is actually 2 Vi1 minus 2 Vi2. So if you add this up, right? So what is Vy? Vy is this value, right? If I multiply 2, this will be 2 Vi1 minus 4 Vi2, then plus 2 Vi2. So what will happen? Ultimately, this will be 2 Vi1 minus 2 Vi2. So this will be actually 2. Okay, so it is actually 2, right? So yeah, 2 is your answer of this question. Okay, just a small mistake on my behalf. So now finally we are done with double E questions, because I took almost all the questions that came recently from double E. Now let's solve this question, right? So this is a 2025 EC question. Which of the following statements is / are true with respect to an ideal op amp? It has infinite input impedance. Yes, it certainly has infinite input impedance. It has infinite output impedance. No, it has 0 output impedance, right? Output impedance would be very low. Okay, 0. It has infinite open loop differential gain. Yes, op amp is used as a differential gain device, so it should have infinite differential gain and 0 common mode gain. 0 open loop common mode gain and infinite open loop differential gain. It has infinite open loop common mode gain. No, it should have 0 open loop common mode gain. So option A and C are your correct answers for this question. Let's solve the next question. This is the next question. All the components in the band pass filter given below are ideal. The lower 3 dB frequency of the filter is 1 megahertz. The upper 3 dB frequency of the filter is what? So lower 3 dB frequency is 1 megahertz. So is this a band pass filter? Can we confirm that? So let's see what is happening in high frequency. In high frequency, this is shorted, right? So essentially, if virtual short is valid, your V out is 0, right? Because this is shorted, so your V out will come here, and it will be equals to 0. At high frequency, V out is equals to 0. At low frequency, this will be open circuit. This also will be open circuit. So if this is open circuit, what is happening? No current is coming from here. No current is coming into the op amp. No current is going into the op amp. So whatever current, right? So essentially this and this are in series. So essentially again no current flows through the resistor. So this also has a 0 drop. So your V out again comes here at this point, which is again 0 volts. If you are not able to understand whatever I said, that means you will have to revise. You will have to revise few things. Okay, so we can see at high frequency and low frequency the gain is 0. V out is 0. For a finite input, V out is 0. Now what happens? So how do I define this? So we can take help of Laplace transform. Certainly you can take help of Laplace transform. Laplace transform and define this filter. Okay, so if I define this, right, so here I have, let me define, so we can apply the virtual short concept. So this will be grounded, so it will be Vs 0 minus Vs 0 minus Vs divided by 1 by 10 Cs. Zero minus VO. Okay. Okay, this will be actually not, yeah, 0 minus, so this will be actually minus VO divided by 1 by CS plus minus VO divided by 2R equal to 0, right? So we got this. Now this would be equals to if I solve for this, right, so VO over VS shall be equals to, okay, just let's not simplify this much. This will be, so your minus of VO CS plus 1 by 2R is equals to VS into 10 CS divided by 1 plus, sorry, not 1, yeah, 1 plus 10 R CS. So yeah, now if I solve it, your VO over Vs would be equals to 20 RCS upon 1 plus 2 RCS 1 plus 2 RCS 1 plus 10 RCS, right? So that is the scenario here. So Yeah, now I think you can do it. So basically, right, what will be, so they have told me what is my uh the lower 3 dB frequency is 1 megahertz. Which one will be lower 3 dB frequency? So I have two poles, right? One pole is at minus 1 by 2 RC and the other pole is at minus 1 by 10 RC. So certainly lower 3 dB frequency basically means this one, right? So they have given me one, they have given me 1 by 2 RC value, or let me calculate this. So 1 by 2 RC. Okay, just okay, this is 10 RC, 1 by 10 RC. This is nothing is changed, everything is same. Hold on. Okay, I have just made a small error. This will not be 1 by CS, this will be 1 by 0.1 CS, correct? So 1 by 0.1 CS is essentially 10 by CS. Okay, just a small error on my behalf. So this will be by 10 actually here. So if this is 10, things might change. Okay, so this will be 10 into, okay, 10 into 220, 20 into this is 200. So additional 10 will be going there, and here also I need to multiply this by 5, correct? This I need to multiply by 5, this I need to multiply by R. Okay, this will be 5 plus RCS, just a small mistake. So what is the higher 3 dB frequency and lower 3 dB frequency? So let me draw the Bode plot, then you realize what do we mean by higher 3 dB frequency and lower 3 dB frequency. So it is basically omega h and omega L. Okay, higher cutoff frequency and lower cutoff frequency. So I will have two poles, right? One, so this is like a band, this is the frequency response of a band pass filter. So I have a pole here, I have a pole here, FH, right? So we have a higher 3 dB frequency and a lower 3 dB frequency, correct? So yeah, now you can solve it basically. So they have given us what is the lower 3 dB frequency, it is 1 megahertz, right? So your FL would be basically, this value would be the lower 3 dB frequency, that is equals to this value 1 by 10 RC. This is in radian per second, right? 1 by 10 RC is in radian per second. Of course you will have to divide by 2 pi, that will give your value in hertz. Okay, just be careful, this will give you value in hertz. And you might say, sir, this is negative, how are you writing frequency? So there is a concept in Bode plot that I have taught in control systems, that poles are negative, yes, true, but frequency is an imaginary term, right? So let's not go into that for now, just assume that this is my frequency, that's all. Okay, so 1 by 2 pi 10 RC, and this is already, that concept is taught in control systems, but this is not the point where we discuss about this. Okay, this is not the time to discuss. So from this value is given as 1 megahertz, so this will be 10 raised to the power of 6. Okay, yeah, 1 megahertz 10. Okay, this is already in megahertz, let's keep it in megahertz only. Let's keep it in mega. So this is 1 mega, right? So 1 divided by 10 RC divided by 2 pi is 1 mega. So what about your higher 3 dB frequency? Higher 3 dB frequency. So your higher 3 dB frequency, higher 3 dB frequency is 5 by 5 by RC, 5 by 2 pi RC, right? So essentially what I need to multiply here, I need to multiply this by 50. If I multiply this by 50, I will get 5 by 2 pi RC, that is 50 megahertz. So your answer would be 50 megahertz. The higher cutoff frequency would be 50 megahertz. Pretty beautiful, simple question, but yet a very effective question. Okay, so op-amp is a very important topic. I'm only taking the 2025 questions. I think 2024 op-amp did not came from, I think very less amount of op-amp questions came, and till 2023 most of the questions have been solved by Himanshu sir. So I did not solve them. Okay, so yeah, this is the next question, where a 4-bit weight register DAC with inputs B3, B2, B1, B0 are given, is designed using an idle op-amp, right, as shown below. The switches are closed when corresponding input bits are logic 1 and open otherwise. when the input B3, B2, B1, B0 changes from 1110 to 1101, the magnitude of the change in the voltage VO would be. So when the input bits are 1110, 111 basically mean the switch is closed, and 0 basically means it is open. So 1110, that basically means that B3, B2 and B1 all will be on, right? And it is simply a DAC. So in DAC what happens? Our voltage uh, ranges from 0 till 2. Okay, and how many divisions are there? There will be total of 16 divisions, because I have 4 bits. There will be total of 2 raised to power 4, that is 16 division. So what is the value of each small scale? What is the value of each small scale? So the value of each small scale would be the scale divided by 2 raised to power n minus 1. Okay, that is the that is how we compute the resolution. Am I correct? Sorry, 2 raised to power n only, right? Not 2 raised to power n minus 1. 0 till okay, no, 2 raised to power n minus 1, because I will start from, no, it will be 2 raised to power n only. Yeah, it will be 2 raised to power n. Okay, that is the value of each small scale. So yeah, here this will be 1 by 2 raised to power 4, that is 16, right? So 1 by 4, that is 0.25. So if I toggle B naught, right, so it gives an incremental value of 0.25, and it depends on one second, it depends on scale. Okay, if you don't know the basic so okay, let me first solve with basics. Don't know anything, right? Don't know anything regarding DAC, don't worry, no need to know anything. Solve op amp, don't worry, just solve op amps. Okay, don't worry. So they are telling me that B3, B2, B1 all will be on, so they will be all switched, they will be all shorted. Okay, so from here what can I say? This will be, this 0, so 2 minus 0. So if I solve for this, if I apply a KCL at this node, this is open, right? So 0 minus 2 by R plus 0 minus 2 by 2R plus 0 minus 2 by 4R, and plus this is 0, right? This is open, plus this value 0 minus VO by R equals to 0. So this shall be equals to, VO will be equals to, R will be cancelled, minus of okay, just give me 1 second, by R, right? Minus of 2 plus 2 by 2, that is 1, plus 1 by 2, that is 0.5, and yeah, that's all. So it is equals to minus 3.5. Okay, that is what your initial voltage is equals to, right? Initial voltage. What is your final voltage? I mean voltage in the second case, in this case. So in this case what is happening, VO2, what is happening? So your switch B3 is on, B2 is 1, and B0 is 1, right? So B3 is on, B2 is on, B0 is on. Now how will you solve it? How will you solve it, right? So same method we will use. So this will be, 2 minus 0 by R plus 2 minus 0 by 2R plus 2 minus 0 by 8R, not 4R, 8R, because the other switch is closed. Not 2 actually, this will be 0 minus 2, right? 0 minus 2, KCL in the inverting node by 8R. Okay, and that is equals to basically your VO2, and a negative sign also will be there, that is there, VO2 by R is there, right? So your VO2 is equals to minus 2 minus 3 minus 3.125 minus 3.125, correct? Sorry, is it, sorry, it is 1 by 4 minus 3.25. So what is your delta V? They have asked the magnitude, they have not asked us the exact change, they have asked the magnitude. So change would be final minus initial, that will be the change in the output voltage. So that would be equals to 0 point minus 0.25. Okay, oh no, it is, sorry, it is plus 0.25 only. So yeah, it is plus 0.25 only because voltage has increased now. So it is plus 0.25, which is positive. So yeah, they have asked in millivolts, right? Remember, they have asked in millivolts. So don't make this mistake. So 250 millivolts shall be your answer for the question. Okay, 250 millivolts shall be your answer for the question. Now, how do we solve using this? So it is, you can understand it like a very basic DAC concept. Okay, so each bit it is like a weighted register DAC. So each switch will consider a weight of raised to the power of 2 depending on the scale. So this will have a weight of what? 2 raised to power 0. This will have a weight of 2 raised to power 1. This will have a weight of 2 raised to power 2. This will have a weight of 2 raised to power 3. Now what is the full scale value actually? That is what I missed previously. Here I was doing something wrong. I was calculating this. What is the full scale value? So full scale value, if we see, if all the switches are on, the full scale value is not actually equals to 2. Okay, full scale value actually is equals to 2 point, so minus 3 point, I'm guessing it is minus 3.75. Okay, if all of these are on, full scale value shall be, so this will also provide 0.25, right? Previously it was 0.35. Yeah, if all of them are on, they will provide minus 3.75. So your full scale value is minus 3.75, correct? So now I will divide this by the number of divisions. Okay, that is minus 3.75 divided by 2 raised to power 4 minus 1. This is the formula of a standard DAC to calculate the resolution. So if I see the resolution, why minus 1? Because minus 1 will be included because 0 was in the range. So if I divide this, right, so if I don't consider the sign for a minute because they have asked in magnitude, this will be 3.75 divided by 15, that is 0.25, right? So what am I doing? Essentially I am just I'm closing this switch, right? So what is the weight of this switch? That is 2 raised to power 1 into the resolution. So 2 raised to power 1 into the resolution, that is 0.25. The weight of this switch is 0.5 volts. So if I close this switch, 0.5 volts will be gone. It will become 0 volt, right? If the bit B1 has been changed from 1 to 0, and if bit B0 has been changed from 0 to 1, it will provide me a voltage of 0.25, because what is the weight? Weight is 2 raised to power 0 into the one small scale value resolution, that is 0.25, right? So the difference would be 0.25. Don't worry if you did not understand, because that is not the purpose. There is a basic method to solve, right? I've already solved this. For the students who understand these things, they will be able to solve this in a bit faster manner, but I will recommend go by basics. Don't go by these methods. This method is working here, it might not work in some other question, but your fundamentals will always work. So with this we are done with the op-amp questions. Now we will start off with our BJTs. Let's begin with BJTs. So this is the first question, and before starting BJT, I want to say, like, most of you guys are scared regarding BJT. I can see you safely 90% of the questions you will be able to solve with DC analysis of BJTs, and that is pretty simple. There are certainly two equations, right? One is for NPN, another one is for PNP. So for NPN, your VBE, right, if it is forward bias, just understand the region of operation. Revise that. What is the region of operation, right? Your, if it is forward bias, your VBE would be equals to 0.7 volts. Why? Because as you can see, this is a PNP transistor actually. Okay, if it was NPN, right, basically what happens, the forward bias voltage of any standard diode is 0.7 volts, right? That's why in NPN transistor your VBE is plus 0.7, and in PNP transistor, if it is forward bias, okay, if this junction, if your base emitter junction is forward bias, then the voltage would be VEB, that would be equals to 0.7 volts. The emitter will be at higher potential. Why? Because your emitter now is P junction, P, and your base is the N junction, N, right? That's why emitter must be higher potential. That's why for PNP it is different. Also, this is the another equation, that your IC collector current is equals to beta into IB, and your collector current is equals to beta into IB, and your IC plus IB is equals to your emitter current, right? If you see, this equation will always be valid. If you see, this is your emitter current, and this is your this is your base current, and this is your collector current, right? And similarly, when things will be swapped, this will be NPN. So now this will be your base and emitter junction, okay? And this will be your collector current, this will be your base current, and this will be your emitter current. This equation will always be valid, and this equation also will be always be valid. Okay, these are few things that you need to remember for DC analysis or biasing of a BJT. That's all. With this, we will solve most of the questions, and you can revise this part. Region of operation of BJTs, right? When it is in saturation region, when it is in cutoff region, when it is in cutoff region, when both these junctions are reverse bias, then it is in cutoff region, right? When it is in saturation region, when both these junctions are forward bias, okay? When this is in active region, during amplification, right? What happens during amplification? Your base emitter junction will be forward bias, your collector base junction will be actually reverse bias. Okay, you can go and revise all these things, you will see this. Yeah, so let's solve this question. In BJT circuit shown, beta of PNP transistor is assumed to be 100. Beta of PNP transistor is assumed to be 100. Assume VBE is equals to minus 0.7, right? Basically they're telling you this potential, or you can say it is VEB is equals to plus 0.7. So this potential essentially is 0.7 volt, right? P will be at higher potential than N. Okay, yeah. So RC, the voltage across RC, whose resistance is 3.3 kilo ohms, will be 5 volt when R2 is equals to what? Okay, okay, so these voltage needs to be, the voltage across RC needs to be 5 volts. Okay, the voltage across RC needs to be 5 volt, right? So if it is 5 volts, then what shall be the what should be the resistance value, right? Yes, so what shall be the resistance value? How can I say what is the resistance value? So what is this current? This current will be 5 by 3.3 in milliamperes, right? And do I know this current? This current would be your IB, correct? And this is your IC current. So I certainly know what is my IB current, because they follow this relation, right? IC equals to beta into IB. So your IB current would be IC by beta. So IC is 5 by 3.3 milliamperes. Don't worry, I'm not writing units, but that is fine. Into beta, beta is 100, right? So your essentially your IB is 1 by 3.3 into 20, 20, this is 33, 33 into 2, that is 66 milliamperes. Okay, 1 by 66 milliamperes, right? This is your uh, base current. Now uh, I know my base current, right? So what is I know this current, I know this current. If I know this current, correct? If I know this current, certainly I know my emitter current. Emitter current is nothing. Actually, if you rewrite these equations, right, your emitter current will be beta plus 1 or 1 plus beta into base current. Okay. So your emitter current will be basically IE would be 101 divided by 66 milliamperes. Correct? That is your emitter current. Now, if I solve for this further, just give me 1 second. Uh, uh, yeah, this is fine. This thing was not charging. Yeah, sorry. Just give me 1 second. One moment. Let me charge the phone. Yeah. If I know the emitter current, then certainly I know this drop. Then what can I do is, if I know this drop, I can apply a KVL in this loop. Correct? So R2 value I don't know. R2 value I don't know. What is R2 value? I do know what is R1 value, right? Will that help me in any shape or form? This current I don't know. But if I know this voltage, this current, I can calculate this current. Yes. Okay, this seems like a bit lengthy, but we will solve it. I'm just thinking what is the easiest way to go about this. If I apply a KVL here, right, there will be two unknowns, current into resistor. So first of all, let us calculate this current. Let us calculate what is this current, right? So this current would be equals to this IR1 plus IB. Correct? IR1 plus IB. So what? How do I calculate IR1? So what you can do is you can simply apply a KVL in this loop. Apply a KVL in this loop. So I certainly know what is this current, IE into 1.2. So if I apply a KVL in this loop, right, that would be minus 0.7 plus 1.2 into IE, that is 101 divided by 66 milliamperes. Then plus IR1 into 4.7 equals to 0, right? So this would be equals to 1.2 into x divided by 66 minus 0.7 divided by 4.7. It is in negative direction. Okay, so your current comes out to be in negative direction. Oh, okay, sorry. Okay, one small error. I have made the voltage across RC. Oh, no error. No error has been made. Everything is fine. I was just worried. I have made a very small error, but that is everything is fine. So interestingly, this current is coming out to be negative. It should not be actually. Why is it coming out to be negative? This will be greater. So if I apply KVL, oh, this is minus. Then this is plus 1.2. Oh, sorry, this will be negative, right? Sorry, current is going in this direction. This will be minus. So, and this is minus, plus minus, and this is plus. That is fine. So ultimately, if I solve for this will be 101 divided by 66 into 1.2 plus 0.7 divided by 4.7. So this comes out to be your IR1 comes out to be 0.534 milliamperes. Okay, so that is what your IR1 is equals to, correct? That is what your IR1 is equals to. Okay, so yeah, now if I solve for this, so I know IR1, I know my IB, so I certainly know what is my this current, right? This is IR1 plus IB, current through the R2 resistor. So it is IR1 plus IB. So IB is uh, 1 by 66 milliampere. That is very low. So it is almost equal actually. It won't even matter. So it is almost 0.554 milliamperes. And this, right? Okay. Okay, there is simply a voltage division happening over here, right? But still that would not help me to find out the R2 value. Now you can apply a KVL in this loop. Apply a KVL in this loop. Okay, so this would be minus 12 plus IE into RE. So minus 12 plus IE into RE plus 0.7 plus this current, right? IR2 into R2, that is equals to 0. So this is equals to your I. So yeah, I know IR2, so I have to calculate my R2, right? So IR2 is 0.554, that is equals to this value. Okay, so IE into RE, what is IE into RE? That shall be 1.2 into 101, just the previous value basically, divided by 66. So this into RE I have already done, and plus 0.7, then subtract this from 12, divide by 0.554. So your R2 actually comes out to be 17.08 kilo ohms. Okay, so yeah, I do agree the calculation is a bit lengthy, but you will get to your answer if you are able to solve using basics. Okay, you will get your answer. So R2 would be 17.08 kilo ohms. Okay, let's solve the next question. So the Zener diode in the circuit has a breakdown voltage of 5 volts. The current gain beta of the transistor in the active region is 99. Beta is 99. This Zener diode has 5 volt as when it is in the breakdown condition. Ignore the base emitter voltage VBE drop. So there is no VBE drop. Ideally, you assume it to be 0. The current through the 20 ohm resistor in milliamperes shall be what? What is the current through the 20 ohm resistor in milliamperes, right? So okay, so if this is plus, right, then this point potential will be higher and this is some minus potential, so this point potential will be lower. So I can assume that the ideally this has 0 cut-in voltage, so I can assume this particular junction to be in forward bias. Okay, so this is a NPN BJT, right? So I see this N side is at higher potential and P side is also at higher potential, but there is some drop, right? So certainly this P point will be at lower potential compared to N. So certainly this particular junction will be reverse bias and this particular junction will be certainly forward bias, because you see there are more resistors here, right? And this anyways is the lower potential. Okay, So we can assume that, let's assume that, yeah, so BJT is in active region. So if BJT is in active region, I can use the equation. What equation? The collector current will be equals to beta into the base current, correct? So if I use this equation, and if some current flows through it which is greater than, so whatever current that will flow, right? So current will flow like this, and if this current, if this drop across this 10 ohm resistor is greater than 5 volt, then of course this zener diode will breakdown will occur in the zener diode. Let's see whether it will happen or not. So let's first assume that there is no breakdown in the zener diode. Let's first assume that it is only open circuit. If I assume this to be open circuit, what is the potential? If it is greater than 5, then certainly there will be breakdown in the zener diode, because this does not have any potential drop. So ultimately this plus minus whatever potential comes, that will be totally coming across the zener diode, and we know the zener diode will be broken down when the voltage across it is greater than 5 volt. So it will remain at 5 volts. It will take some current. So let's see the case here. So if I assume this circuit for a second, right? If I assume this circuit for a second, what will happen? Your okay. Let me assume this to be VB, correct? If I assume this to be my VB, and if it is forward bias, this also will be VB, and if this is VB, right, this is, let's assume this as reference. So this potential would be 2 VB by 3, okay? 2 VB by 3, okay? So yeah, now how do I solve it? How do I solve it? So what is the current in the, so this is my emitter, right? What is the current in the emitter? Current in the emitter is basically VB divided by 30, correct? And I know that we certainly follow this relation, that your IB is equals to sorry, IB into 1 plus beta is equals to IE, correct? So yeah, from this we can certainly solve it. So because beta is 99, so your IE would be 100 into IB, and that will help me actually, because what is your VB actually? Your VB, if you observe carefully, your VB is basically 25 minus the drop. What is the current? It is nothing but the base current. This is open circuit, right? It is nothing but the base current. So that is IB into 7 kilo ohms, right? IB is in milliampere, so it won't matter. It is in proper units. So VB is this value. Right? So let me replace VB here. Let me replace IE with IB. Cool. So VB would be 25 minus 7 IB divided by 30, and your IE is IB is equals to 100 into IB. So yeah, we can actually calculate for IB. This will be 3 into 10 raised to power 4, which is quite a lot, into IB, and this is 25 minus 7 IB, which won't matter, because 3 into 10 raised to power 4 minus 7 would be not much of a difference. So your IB actually approximately would be, I can just make few approximations. If I take 100, this will be 1 by 30, and 1 by 30 into 100 into 4. Okay. So that would be that would be that is my IB basically. So we got our IB. Yeah, now what do I want to? So if I know my IB, certainly I know my this potential drop across the 10 ohm resistor, that is simply what? Uh, the drop across this 10 ohm resistor is simply IE into 10, right? What is IE? IE is 100 into IB. IE is 100 into IB. So the drop across the 10 ohm resistor would be IE into 10 simply. So IE is 100 into IB. So this is 1 by 120 milliampere into 10. It is in milli, right? Okay. 100 into this, it is already in milli. Okay, sorry, this is not in kilo actually. Sorry, this is not in kilo, right? This is not in kilo. Sorry, this 7. Okay, this 7 is in kilo. Okay. 7 is in kilo. Cool. 7 is in kilo. So if your IV is in milliamperes, this 7 and kilo will be automatically gone because it won't make much of a difference. Okay, just one small error. This is not 10 raised to power 4, right? This is 3 into 10 raised to power 3. Okay, so if I subtract 7 for this, this will be approximately, if I take 100 common, this will be 30 and by 4. Yeah, this will be actually 4. Sorry, just a small calculation error from my behalf. 30 into 4. So yeah, now this will be 100 into this, right? So 100 into IB. Sorry, 100 into, yeah, IB, that is your IE into your resistance in kilo ohm, because your current is in milliamperes, right? Your current is in milliamperes. So I have to write the resistance in kilo ohms, that is 10 raised to power minus 2. Because your current is in milliamperes, you will have to write in kilo ohms. So this essentially will be equals to simply 1 by 20, 1 by 120, right? Which is again less than 5 volts. So certainly your Zener diode is not in what do you call, hold on a second now. This in 20, 30 will be gone there. 3007 IB is in milliamperes. Just give me 1 second. Oh, okay. 100. Okay, so sorry. Actually, now let's not do it. Otherwise, I'll okay. Let's not do kiloamperes and milliamp, because this 30, right? This 30 is in ohms. Okay, and you're writing here in kiloamperes. That will cause some problems. Okay, so just be careful. Basically, so yeah, let's not do it actually. Let's keep it simple. Otherwise, I know you are already getting confused. So let's keep it at kilo ohms. Okay, I will be able to handle it, but you will not be able to handle it. Okay, so if it is in kilo ohms, this will be at kilo ohms only. So your IB now is in amperes. I'm sorry, I'm changing this multiple times because your calculation must be very good. Okay, so now things will be a bit different here. So now I cannot ignore it. Okay, this will be 7 into 10 raised to power 3 into IB. Okay, that's what I think I was missing. So now your IB into 10 raised to power 4 would be equals to 25. Okay, it is in amperes. Remember, your IB is in amperes. So your IB actually is equals to 100. I can take 1 by 400. Okay, in milliamperes, this would be 2.5 milliamperes. Okay, I'm sorry, I'm extremely sorry for changing this back and forth. So your VN would be IE into 10. So IE would be 100 into IB, that is 250 milliamperes into 100 into 10 ohm. Okay, so this will be 2500 millivolts, right? So that would be equals to 2.5 volt. So you're sorry about that, again I'm sorry. So your voltage, right, is 2.5 volts. The voltage across the Zener diode, if I assume it to be off, is 2.5 volts, which is certainly not enough for breakdown to occur, right? So it will behave as open circuit. The circuit will not change. Whatever my assumption was correct. As my voltage drop is not greater than the breakdown voltage, certainly this will remain at 2.5. So certainly what have they asked? They have asked me the current through the 20 ohm resistor in milliamperes, that is simply the current IE, and IE is simply equals to I is equals to 250 milliamperes. Okay, that is what your IE current is equals to. This is your answer for the question. Okay, so yeah, bit lengthy, I do agree, both the questions were bit lengthy, but not that difficult. Just I was confused in this kilo ohms and ohms. So like you will always have the option to recalculate. So make sure you write everything properly so that you can recalculate back again, right? So do all these things properly. A BJT biasing circuit is in the figure is shown where VBE is this value, beta is this. The quotient point VCE and ICR. Quotient point basically means the current operating point, right? What is the potential VCE and IC that is currently happening in the circuit? Okay, VVE is given to me. Let us see that whether this will work as a open, this will work as in the active region, cutoff region, or in saturation region, or inverse active region. Correct. So if I assume this to be in cutoff region, what is happening? There is a potential drop between these two resistors, which is this voltage will be what? This will be 12 into 50 divided by 150. So 12 divided by 3, that is 4 volt. And if I assume this to be cut off, right? So there is no current. So essentially this 4 volt is coming across the base emitter junction. So certainly your VBE will be forward bias. That is certain. Your VBE will be forward bias. Okay. Now what will happen? What will happen to your collector base junction, right? Collector base junction. So if I see this is my N, this is my P. If you assume this BJT to be off, so no current flows, so this N point has 12 volts and this point has how much volts? 4 volts. Certainly your N is at higher potential than P, and even if some current flows, then also this N will be at higher potential than P. Certainly this collector base junction will be reverse bias. So this is in active region. If it is an active region, then we can use the relation your IC would be equals to beta into IB. Okay, IC is equals to beta into IB, right? Okay, so yeah, now we know that it is certainly in our active region. So if it is in active region, I have to compute a VCE and IC, right? So so this potential is 0.7, and we know that, okay, what else do you know? This potential is 0.7, and this current is IE, that is simply 101 IB. This current is 100 IB. Okay, this current is IB. What else can I know? What else can I do? So okay, I know this potential, right? This what will be the potential drop across the emitter resistance? That would be 101 IB into RE, that is 1 only. Okay, if I assume IB to be in milliohms, if everything is in kilo ohms, right? All the resistors are in kilo ohms, so here I can safely assume to be in milliohms, right? So this will be 101 IB. Now if it is 101 IB, the potential here is 0.7 plus 101 IB. Correct. So yeah, now if I solve for this, right? If I know this potential, I can certainly know what is the current through this particular resistor. That would be what I know the voltage, right? I know the voltage here. So I can compute the current. That would be 0.7 plus 101 divided by IB divided by 50. Okay, that is the current. I don't even need to know this current. Do I need to know this current? Do I need to know this current? Just thinking about that. Why do I need to know about this current? To calculate the potential. Yeah. So I have understood about this. Okay, I know the potential at this point, right? What is the potential drop here? For that I will need the current here, which I don't know. Okay, but I do know this has 12-volt potential. I know the current here. I know the current here. I know the current here. Right, that is equals to I. Correct. So some current will come from here. The same current will come back down to the battery. How do I come? Okay, yeah, I know this current, right? I know this current. So I certainly know this current. If I know this current, okay, that is this plus IB. So what is the current across the resistor R1? That would be this plus your IB. So that would be equals to 0.7 plus 151 IB divided by 50. Okay, that is the current through the resistor R1. Now I can apply a very basic KVL from here till here, ground voltage source to ground. So that would be equals to minus 12 plus IR1 into 100 plus plus IR2 into 50. That is equals to 0. Now IR1 into 100 would be this into 2. So that would be equals to minus 12 plus 1.4 plus 302 IB plus IR2 into 50. IR2 into 50, right? IR2 into 50 would be 0.7 plus 101 IB. Equal to 0. So yeah, now this would be equals to 12 minus 2.1 divided by 403, that is equals to IB. Okay, so 12 minus 2.1 divided by 403, that is my IB. If I know IB, what have they asked actually? They have asked IC, right? So I know IB. IC would be beta into IB, so that is 100. Everything is in milliamperes. So your IC is actually 2.45 milliamperes. Okay, that is approximately 2.46. That is approximately present in option B and option A. Okay, so we got our option B and option A. Now we have to calculate VCE. What shall be VCE? So VCE will be, if I apply KVL here, right? So 12 minus 12 plus IC into RC plus VCE plus IE into RE, right? That is equals to 0. So your VCE would be equals to 12 minus IC into RC. IC is 100 IB, right? and yeah, 100 IB into RC. RC is 2 kilo ohms. So this shall be 200 into IB, 200 into IB, and 101 into IB, 101 into IB, right? That is equals to 0, correct? That is equals to 0. So sorry, this is the value, right? So I know what is my IB. So this is essentially minus 301. So 301 into IB. Your IB is essentially 2.45 divided by 100, and this minus plus 12, just 4.625 volts. 4.625 volts is present in option A. So option A would be your answer for the question. So mostly BJT questions are they come from DC biasing and they are calculative. We are saying they are pretty calculative. AC analysis very rarely they have asked. They can, obviously it's in the syllabus, they can, but very rarely they have asked for AC analysis. Okay, this question came from BJT and GATE 2025. In the circuit shown, the identical transistors Q1 and Q2, they are identical, biased in active region. So they are biased in active region. I don't have to worry about that. With beta equals to 120, the Zener diode is in breakdown region. VZ equals to 5 volts. So they are already telling me. Sorry, the Zener diode is in breakdown region with VZ equals to 5 volt and IZ equals to 25 milliampere. So this information is already given to me, right? So this voltage is actually 5 volt, and the current through the Zener diode IZ is 25 milliamperes. Cool. IL is 12 milliamperes. So a lot of stuff is given to me. VEB1 and VEB2 are all 0.7 volts. So this is 0.7. This also is 0.7. Then the values of R1 and R2 rounded off to 1 decimal places in kilo ohm are respectively what? Okay. So yeah, what is the value of R1 and R2? Correct. So if I solve for this, your R1 and R2, right? R1 and R2. How do I solve? I have to find R1 and R2. So I know IZ. I know this IZ current, correct? And this current is the what is, okay, this current is not actually, this current is the emitter current of transistor Q2. Okay, the emitter current of transistor Q2, right, IE2 shall be equals to beta plus 1 121 into IB2. All this will help me only. Okay, yeah. I don't think I need this. Oh, okay, this is one information that is good to know. I know IZ, right? Okay, I know IZ. Do I know IL? IL is given to me as 12 milliamperes. If I know IL, what is this? This is the collector current of transistor Q1. So do I know what is IB1? This IB1 current. So IC1 would be equals to beta 1 into IB1. Okay. So IC1 would be equals to IC1 would be equals to IC1 IC1 is this, right? 12 milliamperes, correct? So 12 milliamperes is equals to beta 1, that is 120 into IB1. So your IB1 is equals to 1 by 10 milliamperes. Okay, so I know my IB1, I know my IZ is 25 milliamperes. So essentially your IR1 IR1 is equals to 25 milliamperes plus 0.1 milliamperes. So that is equals to 25.1 milliamperes. Okay, IR1 is equals to 25.1 milliamperes, right? Okay, so just give me 1 second. I got this value. And RL is given to me, right? RL value. Okay, RL is not actually given to me. RL value is not given to me. Okay, that's a bad sign. Okay, no worries. Uh, but what will be why? If I apply a KVL in this loop, that will actually help me. Yeah. So now what I can do essentially, I can apply a KVL in this loop, right? I can apply a KVL in this loop, correct? And that will help me find out the value of R1. I see R1 is different in all four of them. So if I know R1, my question is solved, right? So if I apply a KVL in this loop, so that would be minus 20. Because why minus 20? Because this will be, I can replace this with a simple battery like this, right? Going to ground. Okay, just drawing roughly. So I'll start from here 0, then negative comes first, that is minus 20, then positive comes first, that is plus 0.7, then again positive 5 comes first, plus 5. Simply I am applying a KVL. Then this is the drop, right? That is what? That is IR1 into R1. IR1 into R1. So yeah, that would be equals to 0. So from here I can easily calculate IR1. I already know, so R1 will be coming out in kilo ohms only. So this will be 19.3 minus 5 divided by IR1, that is 25.1. So this actually will be equals to R1 would be 0.56 so 57 kilo ohms, okay, which is approximately 0.6 kilo ohms. So certainly your option A will be your correct answer. Okay, still if you want to solve, right, there is another way. So now you know what is this value, right? You know R1. Now you can apply a KVL in this loop. Okay, let us do that. So do I know this current? Certainly I do. I know what is my IC, I know what is my IB. So your IE1 would be beta plus 1 into IB1, or you can say this will be basically this is 1 by 10, right? So 0.1 plus 12, that shall be equals to 12.1 milliamperes, right? So again applying the same KVL, this would be minus 20 and minus 20, then there is this drop, that is IE1 into R2. Minus 20, there is this drop IE1 into R2, IE1 into R2 plus 0.7, okay, plus 0.7 plus 0.7, then this will go here IR1 into R1. IR1 into R1, that is equals to 0, that is equals to 0, right? So your, I know what is my IR1, I know what is my R1, so I can easily compute my R2. Yeah, just give me 1 second. So this will be 20 IR1 into R1, that will be 0.57 into 26, 26.1, right? This current was 20, so 25.1, and then plus 0.317, that is 15, minus 5. Okay, essentially this was 5 volts only, right? Yes, this was 5 volt. Actually, this whole potential, right? Yeah, I can apply KVL here as well if you want. You can apply a KVL actually here. That also works. What will happen, essentially this 0.7, 0.7 will be cancelled. Essentially the voltage across R2 would be 5 volts only. Okay, you can do it like that as well. Whatever you find comfortable, you do that. Okay, so this will be minus 20, then negative sign, divide by IE2. So IE2 is 12.1 milliamperes, right? So this divided by 12.1 milliamperes, so that is equals to, so your R2 would be 0.413. Okay, not exact, approximate values they have written here, approximate values. So approximate values would be, yeah, 0.4. if you see, they're matching. So option A certainly will be your answer for this question. Let's solve this question. Okay, I think two more questions are left. So this seems like it is from AC analysis, but trust me, it is very easy, not that difficult. A simplified small signal equivalent model of BJT based amplifier is given below. The small signal voltage gain would be, so you just solve the circuit, don't worry about anything. So they have already done the small signal model, all they want is to calculate V over Vs. So you just have to solve the circuit, that's all. So this is my IB, this is beta into IB, correct? So if I apply a KVL in this loop, in the input loop, right? So it will be minus Vs, because if I assume this to be a potential like this, it will be minus Vs plus IB into Rs plus R equal to 0. So from here I can get the value of IB. IB would be Vs divided by Rs plus R and I can apply a KVL in this loop. Okay, so this is not KVL, sorry, yeah, KVL only, right? So VO is what? So this is the, okay, this is not, so here I am measuring the supply voltage, right? So this current beta into IB is flowing from here, beta into IB, right? Because essentially what is happening, you are just measuring the voltage here, right? It is not you are connecting something. So your VO is minus beta into IB. That is what your VO is equals to. Your VO is equals to minus beta into IB, correct? Into RL obviously, because that is the voltage drop. Don't forget the voltage drop. So I know what is my IB, so I can replace that. This would be equals to minus beta into Vs divided by Rs plus R pi into RL. So your VO by Vs is equals to minus beta into RL divided by Rs plus R pi. So minus beta RL divided by Rs plus R pi, that is present in option A. So option A will be certainly correct for this particular question. Let's now solve the last and final question. So again on the DC analysis, the ideal BJT in the circuit given below is biased in the active region with a beta of 100. Okay, it is biased in active region with a beta of 100. Okay, it is already in active region, they have already told us. All they want, if IB is this current, what is VCE, right? IB current I already know. Okay, so if I know IB current, it is in active region, so what will be your IC current, it will be beta into IB. So that is equals to, hold on, this is not the IC current, right? This is my IB current, okay? That is in series. So your IC current is this current. Don't make a mistake. Okay, don't make a mistake. This current is IC, that is 100 into IB. And this current would be what? IB is coming out, 100 IB is coming out here. This is essentially actually the emitter current only, 101 into IB. Okay, and this current also is 101 into IB. So what is happening? I know IB, right? I know IB. So I can actually compute what is the voltage across VCE. So VCE voltage would be, like if you apply simple KVL in this particular loop, it will be minus 10 plus 5 into 101 into IB plus VCE plus 3 into 101 into IB. Okay, that is equals to 0. So yeah, this would be 808 into IB. 808 into IB, right? IB is 10 micro, so I will convert that into milli because every resistor is in kilo ohms, right? So 808 into 10 micro, I will convert this into milli, and then I will subtract that with 10, and that will be the VCE voltage. So your VCE voltage, this one was not that lengthy, your VCE voltage is actually 1.92 volts. Okay, so 1.92 volts would be your correct answer for this question. With this, we are done with our BJT chapter, and I hope you have enjoyed this whole revision, right? So few things we did not cover that you can cover again. The AC analysis of BJT, those things were not covered, and op-amp we did not cover in huge depth, right? I solved all the questions that were asked from EE, and for EC I did not solve that many questions because in the other videos, right, in the other PYQ videos, those are already solved, those are already covered. So it will be again repetitive in nature as that has been already covered, so I'm not covering it here again. So I hope you have enjoyed this video. If you have, make sure to hit the like button, and I will see you in the next lecture. Until then, happy learning.